Welcome, everyone. We're going to start. So the first thing that I want to say is that we're really happy to see you. So welcome to Caltech. I know that for a lot of you, it was a pretty non-trivial trip to come here. So it's really nice to see everyone in the auditorium. There's also many people in the other auditorium, and also welcome to people who are watching us online. So I'm just here to do a tiny bit of bookkeeping, so I'll remind you to please space yourselves out in the auditorium, so there should always be an empty seat in between any two people. Please keep your masks on at all times, and please, there's strictly no eating and drinking in the auditorium, even water. So if you want to take a drink, you have to go outside. The bathrooms are just outside upstairs. Make sure that you know where the closest exits are. So they're just the two exits there at the back. And also, because we're recording the session and we're showing it online, please make sure that your cell phones are completely off for the entire duration of the session. I think I didn't forget anything. So once again, welcome. And I leave it to the session chair, Atul Arora, and Atul will introduce the first speaker. So we have 4 excellent tutorial speakers over the weekend, and I'm sure you're going to enjoy their lectures. So thanks.
Thank you, Thomas. And again, welcome to everyone. I welcome everyone. Today we have with us Richard Küng. I hope I'm not completely mispronouncing his name. He studied and worked at ETH Zurich, Switzerland, the University of Freiburg, Germany, the University of Cologne, and the Free University of Berlin. He's also held a joint position here at IQIM and CMS at Caltech. So we're very delighted to have him here. Currently, he's at the Johannes Kepler Institute, Linz in Austria. And his research is interdisciplinary. It's obviously focused, it's in the area of quantum information and algorithms, computational complexity, but also in applied math that includes convex geometry and high-dimensional probability theory. He has recently done wonderful work in this direction of randomized measurements and harnessing tools from high-dimensional probability theory. And we're very happy to have him here to give this tutorial. I won't take too much of your time, just a few things that I'd like to mention. The first is about the questions. So if you have any questions, I spoke to the speaker a few minutes before this started. So he says he's comfortable in interrupting or it being interactive. So if you have any questions, raise your hand and ask your question. The speaker is going to repeat your question so that people who are online can hear him because there's only one microphone. So that's one quick thing. If somebody forgets, you can always tap me. I'm sitting there, or something. Just make sure that everyone hears the question. That's one. The other thing is about the time. So there's going to be a short gap. So the timing is like from 9 to 10:30. Then there'll be a break, and then from 11 to 12:30 we'll resume. In the short break, there's going to be food, some snacks or whatever outside. You'll find it. It's near the pond. For lunch, people would have to find their own thing. There's a bunch of restaurants. You can ask around. You'll find it. For the masks, Thomas already mentioned that we have to keep them on even if you want to drink and so on. This is not allowed. Like, you have to keep the masks on. This is kind of a mandatory requirement for use of the auditorium. And I think that's kind of it. So, Richard Küng, please take it. Thank you.
So yeah, thank you very much for this kind introduction, Atul. And Thomas, thank you very much for making this conference possible. For me, it's really the first time in more than 2 years to be standing in front of an almost full auditorium, and it makes me really happy. And the only thing that could make me even happier is that it is happening at Caltech, because it also feels a bit like coming home for me. So thank you, all of you, for being here. And I'm very excited and also a bit nervous and to tell you a bit about recent developments in our field that can be broadly summarized under the umbrella term of randomized measurements. And the ideas behind this are actually not new. They are kind of very simple, but they are simple on purpose, because simple things means that they might be possible to implement on the current quantum hardware we have, which is noisy and has restricted functionality, but simple also extends to classical post-processing that we would like maybe to do to make sense of quantum data. So very broadly speaking, I'm going to explain many ideas on how to get near-term quantum devices to talk to normal classical supercomputers in order to help us understand the quantum realm a bit better. And in order to do that, I was giving 2 times 90 minutes of your precious time to take you along on a guided tour. And I want to distribute my talk into 2 parts. The first part will be a lot about intuition, motivation, and we will also actually do a couple of simple proofs in order to convince you how the overall umbrella term, the overall philosophy behind this randomized measurement toolbox works, with the hope to give you the tools to get out and adjust them, if you want to the concrete problems that you and your groups are facing in the era of near-term quantum computing. That's going to be the first part, and it's the first 3 sections actually only. So I will give a motivation, then I will introduce randomized measurements, and then I will also kind of tell you a bit how you can use probability theory, rather simple probability theory, to come up with surprisingly strong convergence guarantees. And in the second part of the talk, I decided to change gears a bit and give an overview over several interesting recent developments within this framework. This will be more high level and is intended to point you towards the right references and maybe interesting problems that are still out there. And I hope that this is a good compromise. And with that, let me start with the actual motivation I have prepared. And we're truly living in very interesting times now. At least for me, it's very exciting, because in the first time in actually forever, we have quantum processors. This is like really a revolutionary technological leap that can make a huge difference, right? Today, we have n-qubit devices that we can reasonably control, and n is of the order of 50 to 100. That's a pretty large number. This is larger than anything we can comfortably simulate with classical computers, right? This is really new, but at the same time, they are intermediate sized. They're not large enough to do the full-fledged far-term quantum algorithms we dream about that Shor and Grover came up with, for instance. And they're also too noisy to do that. But still, because the number of qubits is large enough, they can achieve things that classical computers cannot. So we are an interesting intermediate regime where we have quantum hardware that does interesting things, but it isn't quite there yet to do the interesting things we set out to do, right? And so we're in an intermediate area where we have to think about how we can still make sense of that and take advantage of it and maybe use it to learn new interesting things or to solve problems quicker. But because of this state of the art, in order to achieve that, it's maybe best to couple the qubit processors we have today with powerful classical hardware in order to get the best out of it. And so the algorithms we dream up today, and I think they will continue to be useful, are all hybrid algorithms that I tried to illustrate on the left-hand side, where we have a large CPU, maybe a supercomputer, and this supercomputer can outsource certain computations to a quantum processing unit, to a quantum computer, and the idea is to use this quantum computer to solve complicated subroutines that the classical computer couldn't do. So in a way, it's very instructive, at least for me, to think of current quantum computers as quantum processing units that behave a bit similar to graphical processing units, graphic cards. It's not a fully fledged computer, but we can outsource certain computations to these processing units, and they do them much, much quicker. And that is very much the vision behind most near-term quantum algorithms. And one of them is the variational quantum eigensolver, where you try to make sense exactly of such a hybrid approach. And on a high level, the idea is to learn something interesting about quantum physics or quantum chemistry by minimizing certain energy functions over a large quantum mechanical state space. Quantum chemistry is a good example, but you can also try to probe field theories or interesting quantum many-body systems. And how does it work? It's exactly set up in such a hybrid geometry where, in order to minimize the synthetic energy, that's just a ground state problem, we parameterize a family of quantum states by classical control parameters. And the interesting twist is that we use these small intermediate scale quantum computers to actually prepare these parameterized quantum states on a quantum computer. And subsequently, you use the quantum processor to measure the energy function. This is precisely the computation we outsource to the quantum part, because if we wanted to do that classically, it would be exponentially expensive in the number of qubits, right? And then once we've obtained ideas of the energy and maybe the gradient thereof, we can use the classical computer to do some stochastic gradient descent optimization, some updates to change the parameters to make this value smaller, right? I think most of you are familiar with this setup, and I think it's very promising, and it receives a lot of attention these days. But within each loop, there's actually a problem hidden, right? And I call that the readout problem, because at each iteration, when we outsource the computation to the quantum processor, it produces a state, and then afterwards, we have to perform a measurement to make sense out of it in terms of bits and macroscopic information. And quantum measurements are destructive and probabilistic. And so what we get out is not the expectation value of the Hamiltonian, but it's some plus or minus ones. And we have to repeat that many times to get enough statistical data to estimate the expectation value, it's in the name of the random variables associated, right? And this introduces an additional inner loop that can be very expensive. Because if you do a bad measurement procedure, you have to run this inner loop within each step of this iterative algorithm many, many times to just get an idea what my current energy level is and what my current gradient is. And this can really slow you down because it's within each step of an iterative optimization procedure, right? It's usually polynomial in complexity, but in iterative algorithms, a polynomial slowdown can actually mean quite a lot. And so the question that I want to set out to answer in the first part of the lecture is how can we measure or estimate the terms in such a VQE optimization as efficiently as possible, but efficient in the sense that all the resources involved are bounded. So first of all, I think we should only use modest quantum resources because our current quantum devices, they simply can't perform deep circuits that allow us to do maybe some smart post-processing. We really should do simple quantum circuits to keep the noise effect at the minimum. But at the same time, we should also worry about efficient classical storage and runtime. If we have n qubit systems and n is of the order 100, then data storage can become a real problem, right? You can't store a 2 to the 100 by a 2 to the 100 matrix. You really should be careful there as well. And last, this is the thing I alluded to you already before, we also want to keep the number of measurements we have to do as small as possible, because that's this inner estimation loop that affects the runtime of the overall algorithm, okay? And essentially for the rest of this guided tour I'm allowed to give you, I will tell you some ideas that are not that difficult, that attempt to optimize efficiency in all of these three regards. And I will hope to convince you that this has important practical applications like VQE, but there's also very interesting theoretical and fundamental problems and applications hiding between. Okay, so that's the motivation. And let us continue with a simple warm-up example. It's still a bit early and maybe it's good to get our brains going. And so let's look at a concrete VQE application where I tell you the Hamiltonian we want to minimize is a very simple Hamiltonian. It's essentially a Heisenberg Hamiltonian on a 1D chain with n qubits. It looks like that. How would you measure that? Well, and I will try to convey three measurement ideas to you. The first one is, I call it the direct method. You could also call it the stupid method. It's measuring all of these terms one at a time, right? The first term is x on the first qubit and x on the second qubit, and I could perform quantum measurements as they're illustrated on the left-hand side, just in the first two qubits, forgetting everything else, to get statistical data whose average will give me the expectation value of the first term, right? And then I could do the same, changing bases with a simple 1-qubit unitary on the first two qubits to rotate it into the y basis and do the same thing. I do that all over again, and in the end I have an overhead of 1 over epsilon squared. That's the shot noise. That's the number of samples I need to take to get an epsilon approximation of the energy term. And if I sum everything up, the number of measurements I need scales linearly in the number of Hamiltonian terms. Not surprising, we measure all of them sequentially. This is polynomial in the number of qubits, but it's a very bad idea. And I hope you see that it is extremely wasteful, because we could do something much smarter. We could just measure 3 Pauli observables in a single shot limit and use marginalization to actually get all of these terms. Okay? I think you see that. And if we do that, we get a number of measurements that is proportional to 3 over epsilon squared, because now we only have to do 3 different measurements in the single shot case, parameterized by very simple single qubit unitaries, the same on everyone. And then we get outcomes, plus, minus 1 or 0, 1. And if we marginalize them correctly and average, we can predict all of these terms simultaneously. So we don't see a dependence on the number of qubits at all, right? But hopefully you also see that this is maybe a special case. We can do that because the Heisenberg Hamiltonian is simple. If the Hamiltonian becomes a bit more complicated, finding an optimized method is probably difficult. And this is where the third method comes in, which is the main topic of today's lecture, which is a randomized method. The idea here is to choose to not even think about what to measure, but to just do random measurements. I roll a die, and depending on the outcome, I measure the first qubit either in the x, y, or z basis. I roll another die and decide how to measure the second qubit, either in the x, y, or z basis, and I continue that. Note that this randomized measurement strategy is completely ignorant towards the actual target, towards the actual Hamiltonian we want to estimate. It's just a randomized measurement protocol designed to acquire data. And why is this not a completely stupid idea? Well, it all comes down to probability, right? Suppose that we want to measure one of these terms in the Hamiltonian, then there are 2 local. There's only 2 qubits where the actual measurement matters, and everything else we can marginalize over, right? And if we now sample each of the single qubit measurements randomly, then all that matters, for example, for the x1, x2 term, is that we measure the first qubit in the x basis and the second qubit in the x basis, while everything else doesn't matter. It's about a different qubits, right? And the probability of hitting x on the first and x on the second is not that small. It's 1/3 times 1/3, that's 1/9. So when I sample 9 of these guys independently, then we expect that at least one of these very long random strings give us accessible and interesting outcome data that we can use to estimate the x1, x2 term. And now the twist comes, because nothing I told you about actually depends on the fact that the Hamiltonian term was x1 and x2. I could have told you the same story about x3 and y27. It's also only 2 qubits, and the probability of hitting it correctly is 1/3. And so if we do that over and over again, then with each randomized measurement we choose, we can expect that maybe with probability 1/9, we get any of these 2 local terms, right? And so if we repeat that often enough, we can maximize our chances of getting enough statistical data for all of them simultaneously. And that is illustrated in the picture on the lower right. And if you actually do that and use some probability theory, then you will see that the number of randomized Pauli measurements you actually have to do to get enough statistical data to estimate this Hamiltonian is proportional to 3 squared. That's to counterbalance the probability of 1/9 to actually hit 2 local terms, over epsilon squared, that's again the shot noise part, times a factor that scales logarithmically in the number of terms. And I will later prove or show you where this logarithmic factor comes from. It's a consequence of probability theory, because if we actually want to hit all of these terms sufficiently often, then the overhead we need in terms of samples, in terms of game number of rounds we play the game, is only logarithmic in the number of terms. Okay? And this is now an interesting intermediate regime between the naive method and the optimized method, because now it only depends logarithmically on the number of terms. And this is arguably much, much closer to a constant than it is to a linear function. And we got that basically for free. We don't have to think about what the Hamiltonian actually looks like. Whereas for the optimized method, this is very much important, right? And in order to convey that and to wake you up, I actually want to give you a simple exercise. Suppose I give you a different Hamiltonian that looks like this. Sorry. That is not a very physical Hamiltonian, but you see what I did. I kind of modified the Heisenberg Hamiltonian to make it a bit more cyclic. And now look at this Hamiltonian. Can you think of a direct optimized measurement strategy out of the top of your head? Is there one? Don't worry, it took me a while to figure that out, actually. Yes?
Maybe you should measure like x1, y2, z3, x4, and so on and so on.
You're very good. You were like 10 times quicker than me, but this is the right answer. Yeah, sorry. What he said, he gave the correct answer. Thank you. And I'm going to write it on the whiteboard now. Okay, I hope this is okay. So what he proposed, which is actually correct, is to start with measuring the first qubit in x, the second qubit in y, the third qubit in z, and then the fourth qubit in x, y, and keep going. And if you look at that, you see that this hits the first term here, and for the second two terms, it hits this guy. But it doesn't hit yz or cx yet, but it can make this happen by cyclically permuting the measurement setups. Y, Z, X, Y, Z, and so on, and C, X, Y, Z, X, Y, and so on. And this gives you, again, a collection of 3 different Pauli measurements. And if you look at it, you can figure out for yourself that this actually gives you enough data to estimate all of the terms in the Hamiltonian. And I'm again very impressed how quick you were, because it took me a couple of minutes. And it is intended to illustrate that if we slightly change the Hamiltonian, then this question of optimal measurements becomes a bit trickier. And it's easy, actually, to come up with Hamiltonians where such an optimized measurement strategy just doesn't work. And it is in these regimes where the randomized measurements maybe help, because they already give you an exponential improvement in terms of the number of terms.
Richard?
Yes?
There's 2 questions. One I'm forwarding from online, and the
Yes.
other is mine. They're about to set up on your slides. The first question from online is, when you write measure x tensor n,
Yes.
Do you think that we get n-bit output
Yes.
or a single bit?
Thank you very much. That is a very important question for clarification. I'm now thinking about single shot measurements as they would happen in an actual quantum computer. And when I say I want to measure x n times, then what I mean is that I take the state I'm interested in, and then I do single qubit rotations that rotate the computational basis, which is the z basis, into the x basis, essentially Hadamard. And the Hadamard will turn the computational basis measurement into plus-minus measurements, the plus-minus basis. I will again get an outcome of n signs, plus or minus. And this is the measurements I'm considering. And when you then want to estimate average properties, like expectation values of these Hamiltonians, you look at the qubits that interest you, forget all the other signs, and then you can average them in order to get expectation values. Thank you very much for giving me the chance of clarifying this. What was the second question?
The other question was, I wanted to make sure I understand the epsilon well. So this applies to the direct method. So if I measure each term 1 over epsilon squared times each
Yes.
term would give me an estimate additive epsilon.
Yes.
But then when I add them up,
Exactly. That's true. They could be correlated. But for now, I want to keep things simple. And exactly, sorry, to remind it to the audience as well, what Thomas was correctly pointing out is that if I only ever measure x to the tensor power of n enough times, I can get every marginal, every reduced expectation value up to accuracy plus minus epsilon, but the individual expectation values might be correlated. And so if we do an epsilon error on each term, if you sum them up, this can become larger. This is true, but for now, I want to be happy with saying that we have enough data to measure each of these terms, let's say 10,000 times. And then we can think later how the errors accumulate. Very good point. Thank you very much. Okay, now we already did the exercise, and I can move on. Here, I actually want to use the main part of the first lecture to kind of give additional intuition about how this result actually comes about and how you can prove that a number of single-shot measurements that scales logarithmically in the number of terms you actually want to predict is provably enough to get epsilon approximations of all of them, very much in the sense as Thomas already hinted at. Okay? And in order to keep that a bit interesting, I don't want to do the direct derivation based on quantum mechanics, but I want to change perspective a bit and do it from the position of Monte Carlo sampling, which is a very powerful idea from numerics. I'm sure all of you know that. Monte Carlo sampling is still a powerful technique in big data analysis, physics, and engineering. And you can actually view all these approaches about randomized measurements as a special case, as an application of Monte Carlo sampling. So what are Monte Carlo methods? The Monte Carlo paradigm is very simple. Repeatedly use random sampling to obtain approximate results about potentially difficult problems. The idea is really to use randomness as a numerical tool to get the results you want. And I'm sure all of you are familiar with this famous circle example. If you don't know what pi is and you want to find out, then one way of estimating pi is actually depicted here. You just take the unit interval in 2 dimensions, a square, and you sample points uniformly at random from that square. That's easy. And then for each point, you check if the squared radius is smaller than 1, smaller or equal to 1, or larger. And if it's smaller or equal to 1, you output 1 and 0 otherwise. And because we do uniform sampling, if we do that long enough, we approximately evenly cover the square and have a simple function that doesn't depend on square roots that tells us whether we are inside the circle or not. And if we add up all these ones, we'll get ever more accurate approximations of pi without ever having to take square roots. That's a very good example of Monte Carlo sampling, where you use an average of relatively simple functions to compute or approximate something that is not as simple, like pi in this case. But Monte Carlo methods are still very, very promising and widely used for big data problems. And another example I like a lot is the example of graph sparsification. Like suppose you're given a network, a graph that looks very complicated, like the one on the left-hand side, and it's just too big to analyze with standard numerical methods. Then one thing you could do is to probabilistically remove edges to get a graph that is much, much less connected. So kind of it has much fewer edges, because I kind of remove edges with a certain probability, but with the intent that the underlying graph properties, like connectivity and cut values, are still approximately preserved. And if you want to do that, you can't simply do uniform simple sampling, because if some edges are more important than others. That is hopefully clear to you if you think about it. Maybe you have like one edge that is very important to connect 2 parts of the graph, then you really shouldn't remove that. But you can solve that by doing a biased sampling where you keep each of the edges with a probability that is proportional to a summary parameter about its connectivity. They use effective resistances, and this gives you a slightly more complicated Monte Carlo approximation procedure, because now the edges only survive with different probabilities. But if you do that, you can really do graph sparsification, and this helps you a lot when you want to analyze big data, big networks, and there's like really groundbreaking, amazing consequences of this. One of them is this famous algorithm by Spielmann and Teng to solve Laplacian inverse systems in almost linear time, they actually use ideas a bit like graph classification. And so Monte Carlo is still very much there and is used by people who actually don't have measurement problems or whatever, who just have to deal with very large data that is too big to feed into conventional computers. And then you can use ideas from Monte Carlo to approximate a complicated, very big thing, this bold A. Just think of it as a very big matrix, like the Laplacian of a big graph. And the idea of Monte Carlo approximations in big data is to rewrite your complicated object as a probabilistic average of things that are simpler. This, on the left-hand side, this could be a big matrix, and on the right-hand side, this could be an average of matrices that have additional structure like sparsity or low rank that allows you to speed up your numerical approximations. And then once you found a probabilistic decomposition of A, you can use that to sample exemplars from the distribution which reproduce the original data matrix in your expectation. So once you have this formula, you can sample random matrices, B1 to Bm, independently from this distribution. This is what this line says. And what you end up with is you get samples where each of the samples is much simpler than the original object. But if I take the expectation value over infinitely many draws, I would get the complicated object. And now the trick of Monte Carlo averaging is to approximate this true hypothetical expectation value by an empirical average over fewer terms. And then you can use probability theory to show that ideally these empirical averages converge quicker than you think. And what you end up with is you have a probabilistic approximation, which is essentially a sum of many simple terms, and it still allows you to approximate a complicated underlying object. That's the idea of Monte Carlo sampling in big data. And the benefits is really storage and runtime when you have very high dimensional problems, which is one of the main reasons why people actually use Monte Carlo methods to approximate and process matrices or objects they actually know. So they have a deterministic description of the object, and they still decompose it into a probabilistic sum and sample because it gives you benefits in terms of processing and tractability. And this actually means that also in the classical domain, when it comes to big data, Monte Carlo methods are still very much a thing. What is the bottleneck here? What is the most expensive thing you have to do in order to run such a Monte Carlo approximation for any application that you can think of on your classical computer? Well, it's finding these compositions in the first place and then do sampling, because these probability distributions are typically non-uniform. And if this is a very complicated object, this is a probabilistic probability distribution over very many different simple terms, and the probability distribution varies a lot, and then you have to find ways of actually simulating the random sampling. And this is the bottleneck for classical Monte Carlo methods. And the main intuition behind today's lecture is actually here. Sorry. We talked about quantum computing before and near-term challenges, and I tried to tell you, or I hope you agree with me, that one of the annoying things, or seemingly annoying things, about quantum computing is that we never have direct access to the quantum state representations, to the density matrices. All we can do in an experiment is sample from a distribution that depends on this underlying data density matrix, right? We only have sampling access by quantum measurements to the states whose properties we actually care about. And this was an annoying thing before, right? Because it forced us in within each VQE operation to repeat it many times to get data. But note that it actually by default addresses the most difficult part in a normal Monte Carlo approximation. In normal Monte Carlo approximations designed for big data, like density matrices of many qubits, the bottleneck is the sampling process. And now, when we want to understand quantum states prepared on quantum computers, the only thing we get almost for free is sampling such distributions. And so this points towards a very fruitful combination of quantum measurements and near-term quantum computing on the one hand, and these Monte Carlo methods from big data on the other hand, that allow us to approximate complicated objects like density matrices very efficiently. And these randomized measurements are precisely one way to realize such sampling processes. Are there any questions at this point? Okay, very good. So let us gain some intuition, and I really want to build up to a Monte Carlo sampling procedure that allows us to approximate complete density matrices. And the first thing you might try out, and it's actually useful, is to think how could we start with the n-qubit density matrix and decompose it into a sum of terms that look much simpler. That's the first step in a normal Monte Carlo approximation. And if you are like me, the first thing that comes to mind is the Pauli basis. It's a very, very nice matrix basis that is formed from tensor products of single qubit Pauli matrices, and that means that every Pauli matrix is simple because it's an elementary tensor product. And so if we decompose, we can always decompose every state as a weighted combination of Pauli operators, and the Pauli operators are tensor products, which is very beneficial for numerical analysis and storage. So here we are seemingly in a situation where we start with a very complicated object, and we decompose it into a weighted sum of simple terms. And now the Monte Carlo paradigm would tell us, yeah, well, let's just sample from these weights, right? Let's just try to do the Monte Carlo trick. Let's do samples, independent samples, row 1 to row m, where each row hat is a certain Pauli matrix. This J is a multi-index that tells you which qubit is which Pauli, and probability Qj of rho. And if we could do that, then we are in the Monte Carlo regime, and we could use empirical averages of these simple Pauli matrices in order to approximate the true expectation value, which by construction, because the Pauli matrices are a basis, form the original state rho. Great, right? Is there a problem? Why don't we do that? Very good. Somebody in the audience immediately pointed out, and rightfully so, thank you. This doesn't work because the Pauli expansion coefficients are not a probability distribution, right? These are expectation values of Pauli observables, and they can be positive or negative. It doesn't make sense to sample from a negative distribution. And there's actually another problem as well. It's not normalized. But even if that were the case, I don't want to sample from expectation values. That's somehow the wrong notion. If you want to sample, you want to sample from probability distributions, and the Pauli matrices are expectation values. So even if they were all positive, it's not clear how to use a quantum computer to sample outcomes according to Pauli expectation values. This doesn't quite solve the problem. But still, the intuition has some merit. And one application of this vision is direct fidelity estimation, as it was invented by Steve Lamia and Yikai Liu in 2012. And in the easiest form, what they pointed out is suppose that our rho here is not an arbitrary state, but a stabilizer state. And stabilizer states are very special, because if you look at the Pauli expansions of stabilizer states, then they can only have 3 values. +1 if your Pauli matrix is in the stabilizer, -1 if minus your Pauli matrix is in the stabilizer, and 0 else. And I can discuss the minus sign away by averaging not over Pauli matrices, but the Pauli group. And now I have something that almost looks like a flat probability distribution. And I can try to renormalize that, and then I can try to use Monte Carlo sampling for stabilizer states. And what they pointed out is that this is actually a useful subroutine if you're interested about a state in the lab, rho, and its fidelity with a known stabilizer state. Like you want to check if your friends in the lab actually prepared the GHZ state they promised to prepare. Then you can approximate the fidelity between an unknown state rho and this stabilizer state psi by a Monte Carlo average, but not over the state rho, but the Pauli operators that make up the stabilizer state itself. So rather than directly measuring the fidelity with psi of rho, I decompose psi, because it's a stabilizer state, into a sum of Pauli terms, and then I don't measure all of these Pauli terms, but I only measure the ones that I sample randomly from. And they showed that this converges quickly and allows you to estimate fidelities with stabilizer states in an unknown state rho by essentially measuring only relatively few Pauli observables. And now this is Pauli observables, and we can do that with near-term experiments. So our first attempt at coming up with Monte Carlo sampling approximations for states was not quite fruitful, but it still has important merit and actually explains the direct fidelity estimation protocol. But we're not quite there yet, right? We didn't achieve what we set out to, namely sampling from distributions governed by quantum states. And this is intended for on the next slide. Well, in order to actually get a Monte Carlo approximation, what we maybe should be doing is to really start with our quantum state and perform measurements, right? That's what I promised should be the link between Monte Carlo sampling and quantum mechanical measurements. And so what is the next best thing? We simply don't do any post-processing at all and always measure in the computational basis. So we prepare our state, then we measure in the computational basis, and we get a computational basis outcome, plus 0 or 1 for each qubit. And then the simplest Monte Carlo estimator I can think about is to just perform the measurement and setting rho hat or approximation to be the basis outcome that I actually observed. So I perform a measurement, I get a computational basis string, and then I pretend that this post-measurement state is actually a quantum state, a ket bra, and I just say, okay, this is now my approximation for the underlying density matrix. That achieves the Monte Carlo paradigm of being simple, because each of our independent estimators is now a tensor product of pure states of pure computational basis states. And now I could try to repeat this procedure to do Monte Carlo averaging and learn hopefully something about the underlying state, right? So that's precisely what I'm proposing here. And here we have to be a bit careful, because if we do Monte Carlo averaging, then we approximate the expectation value of this random matrix, of this Monte Carlo sample, and we can write it down. Well, it's the sum over all computational basis outcomes, the computational basis vector as a state, weight by the probability of observing that computational basis outcome, right? And I can use Born's rule to rewrite this in this form. And if you look at that, you will see that this is not the actual quantum state, but it's the diagonal of it. So if I just do computational basis sampling in order to try to do Monte Carlo approximations, I'm not completely wrong. The only thing is that I can only faithfully address the diagonal elements of my density matrix with respect to the computational basis. No surprise there. We only ever measured the computational basis to begin with, right? And this is arguably still a useful or semi-useful protocol because it allows us to accurately approximate observables or properties that are diagonal. Like I can approximate tensor products of the Pauli Z matrix. What I can't do is off-diagonal observables, like Pauli X, for instance. There my Monte Carlo approximations are completely useless, because they will always output 0. But still, the overall idea works, right? We just have restricted vision to the underlying quantum system, and the benefit is that the quantum hardware is very, very simple. We only have to do computational basis measurements. And there's actually a famous application of this Monte Carlo philosophy that you might know as cross-entropy benchmarking. Because what is the idea in cross-entropy benchmarking, which was introduced in a very seminal paper by the Google group in 2019? They actually used that to calibrate their supremacy circuits. But what did they do? Like on a high level, what cross-entropy benchmarking attempts is we want a quantum computer to prepare an idealized state psi, maybe the state after a random quantum circuit. But our actual quantum computer, in this case the Sycamore chip, only does a somewhat noisy implementation or approximation of rho. And now you want to get an idea of how close rho, the thing we actually did, is to the thing we set out to prepare. And what cross-entropy benchmarking suggests is to do Monte Carlo averaging precisely with this type of Monte Carlo sampling. So I prepare my state, I run my noisy circuit, I do a computational basis measurement outcome, and conditioned on the outcome I get, I say my approximation is the computational basis outcome I saw. And I use these Monte Carlo approximations to approximate the fidelity with the unknown, with the idealized state I actually want to set out. This on the left-hand side looks like a Monte Carlo approximation of the fidelity between the idealized state and the lab implementation, right? If the rho hat wouldn't be there. But now, and if we actually go further, and we can just simplify this because our rho hats, our estimators are always the computational basis measurement outcomes we've seen, we actually get that this Monte Carlo average averages the entries of the idealized state psi evaluated on the actual noisy measurement outcomes I've seen. And what you get is now a sum of outcome probabilities of the idealized state that you have to compute classically. This is just when I set up to do this, with this type of Monte Carlo sampling, this is what I actually have to do in my classical post-processing. And what does this approximate? What does this average? If I take the expectation value of this type of Monte Carlo estimator over the computational basis measurement outcomes, then what I see is that I get an average over all computational basis outcomes that exist of the probabilities that I measure the computational basis outcome with when I measure rho times these weighing factors up here that correspond to the same computational basis outcome probability of the idealized quantum state psi. And those of you who are familiar with that, on the very right-hand side, this is proportional to the actual definition of the cross entropy that Google is using. They really try to approximate kind of like the product of the probabilities of the idealized state with the probabilities of the state they estimated in a lab. But if you actually look at the protocol, what they did, it's Monte Carlo sampling with near-term quantum hardware where you use a Monte Carlo approximation that only ever uses the computational basis measurement. And it's tricks from Monte Carlo sampling that allows them to infer that these convergences happen rather quickly. Okay? So already having Monte Carlo sampling only for diagonals of the density matrix can be a very useful goal. Cross-entropy benchmarking is a very popular benchmarking procedure to this day. But still, we shouldn't ignore that it doesn't give us the whole state, but only ever access to the diagonals, right? And so maybe, just maybe, we can do simple updates to our Monte Carlo sampling procedure in order to make sure that we don't only get one diagonal, but all of the diagonals that exist in Pauli basis. And the problem with only sampling in a computational basis is that for each qubit, we only see one direction. And there's 3 possible directions that you would like to see or need to see in Pauli land in order to get a full idea of what the actual density matrix looks like. So how about the following modification of this Monte Carlo sampling problem from the previous slide that directly addresses its drawback? Let's not measure each qubit always in the computational basis, because that restricts our view. Let's choose a Pauli basis uniformly at random by applying a single qubit preprocessing circuit like a Hadamard gate that switches the Z basis to the X basis. And let's do that in a kind of like in a preprocessing step where we first throw a dice to get the measurement settings randomly assigned, and then we perform the actual quantum measurement to sample according to a distribution that now also depends on the underlying quantum system. And because we, in a preprocessing stage, decide whether we want to measure Z, Y, or X, on average, we will see all of them and hopefully get a more clear and complete approximation of the underlying quantum state, right? And so what would this look like? Well, in each step of our Monte Carlo sampling procedure, we prepare the quantum state on our quantum device, but then we roll a classical dices to decide which measurements to perform. Is it X, Y, or Z on the first qubit? Is it X, Y, or Z on the second qubit? And so on. And then we execute that measurement. And what we get now is, again, strings of outcomes, +1 or -1 for each qubit, or 0 or 1 for each qubit. But we also remember which basis we measured in. And now there are 3 possible bases. If we measure in the Z base, it's the computational basis, the X basis, is plus minus, and then the y base is the third one where nobody has a consistent notation, right? But we decide which basis to use for each qubit, and then we execute the associated quantum measurement. And what we get is exactly to get a Monte Carlo sample, and then we do empirical averaging, Monte Carlo averaging, by repeating this simple procedure m times. Each time we prepare the quantum state, sample a new measurement setting, perform the measurement, and remember what we saw in terms of these basis vectors. Okay? And now, when we've seen these type of outcomes, we now have to still think about what should we use as a Monte Carlo approximation of the actual underlying density matrix. And the simplest idea is to adapt the same one from the last page, where when we observed an outcome string S1 to Sn, now each of them has 6 options, right? Because we now measure potentially in 3 bases. Well, when we observe that, we just say the actual quantum state, or our Monte Carlo approximation of this quantum state, is just the post-measurement state, this S ket S bra. This is our Monte Carlo approximation. And if we write that out, then you can see that it's still very, very structured, because each of these terms is really a tensor product of single qubit pure states again, which is good for numerical post-processing. And the Monte Carlo average approximates the idealized, or the true expectation value of this type of Monte Carlo approximation. And this is equal to the probability of obtaining such measurement outcomes S with n entries multiplied with the associated post-measurement states. And if I spell that out in single qubit examples, I will get a factor of 3 to the minus n in front. That's taking into account that we measure x, y, or z with probability 1/3 each. This is a prior probability by us that we have to take into account. But then the rest decomposes really nicely into a sum of single qubit states, because the measurements are uncorrelated, are tensor products, and the estimators are also tensor products. And this is something we can actually compute. And hopefully, it will give us more information than just ever measuring in the z basis or the x basis or the y basis. And in order to do that, here we have a very nice tensor product decomposition. And if you actually want to compute this expectation value, it is enough to do it for a single qubit. And I want to do this computation on the whiteboard, because I think it's actually very instructive. So we have 1 qubit. And that means that the outcomes we can get are either 0, 1, plus, minus, and then these weird y eigenstates where I use this notation, arrow front, arrow back. This is what we can get. And that the probability of obtaining S hat equals to one of these s's here is really just 1/3. This is the prefactor. I had that earlier, times S hat rho S hat. And now we have, sorry, it's really just 1/3 the probability that I actually measure S taken from here. What I do is I do a POVM measurement that is comprised of 3 possible basis measurements, the z basis, the x basis, and the y basis. And now I have 6 potential outcomes. And if I actually measure a single qubit quantum system rho, the probability of getting one concrete outcome is just 1/3 times the Born rule probability for that outcome. Okay? And this is enough to do the Monte Carlo approximation, because we say that sigma hat is S hat, S hat. That's the idea. Our Monte Carlo approximation is, we believe that the underlying quantum state is the post-measurement state after the measurement. And now we can compute the expectation value of sigma hat, and that's really just a sum over all possible outcomes, probabilities of those outcomes times approximations, and this is, and 1/3 in front. And if I put it together, it looks like this. And now you can see that this is like a quadratic polynomials in the unknown s's. And the s vectors, if you view them in a Bloch sphere, are actually quite nice because they are north pole, south pole, then 2 of these and 2 of these. And they are what we know or call a state 2 design. And that means if I average quadratic functions over these types of states, it's the same as averaging the same function over all possible pure states. And so this is equal to 1/3 the average, the H average of psi rho psi, 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 where psi now really is sampled from the H distribution of the entire Bloch sphere. And now you can use techniques called H integration in order to actually carry out this type of integral explicitly using group theory. What I like to do is to rewrite that as a partial trace of a H integral, d psi of d psi, 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 tensor 2, rho tensor identity. And now there's closed form expressions for this type of integral, and it corresponds to 1/3 times the partial trace with something that is proportional to the projector onto the symmetric subspace of 2 particles. And d is 2 here. And if you do the math, what you will get is 1/3 rho plus trace rho identity. And this is a simple depolarizing channel acting on rho. This is what you get. And the nice thing is that because we have a tensor product structure, our Monte Carlo averaging will act like this on all the qubits independently. And so when we actually want to compute the expectation value of this Monte Carlo procedure, we can do that analytically. And what it looks like is the original state rho. It still survived over there. You see it. But each qubit is a bit depolarized. Each qubit is a bit pushed towards the maximally mixed state. And that means that our new Monte Carlo approximator, where we use random polybases in each entry, actually knows about all directions of the underlying quantum state, but it's not quite there yet because it's biased towards the maximally mixed state by a very simple object. But this can be done, this can be compensated for, right? I just have to adjust what I call my Monte Carlo estimator. Our Monte Carlo estimators only live in the classical world, and in the classical world, if I'm giving matrices, I can easily undo a depolarizing channel by pushing the matrices out again, away from the maximally mixed state. And this is what we called classical shadows. And what we do here is we do the same Monte Carlo estimation strategy, but we adjust the Monte Carlo approximation to counterbalance this expected single qubit depolarizing effects on the purely classical post-processing level. And what we get is something that still almost looks like a product state, but at each term, we have to undo single qubit depolarizing channels, and so it looks a bit more complicated. But it still decomposes nicely into tensor products. Each of these tensor products has trace 1. It's not positive semi-definite, but it is designed to give us Monte Carlo approximations that come from this randomized sampling process and that obey, that they approximate the actual true underlying quantum state if I do empirical averaging often enough, because we've counterbalanced the depolarizing effects of the different computational basis measurements, and because with a certain probability we look in each possible single qubit direction on expectation, we will get all of them correct. And this is a substantial improvement over just measuring in a computational basis where you can only ever get one diagonal. Okay? And this is a technique that we actually developed here at Caltech. It was me together with Robert Huang and John, who is here, but it was also independently discovered by Paini and Kalev. That you can use these single randomized single qubit measurements in order to, with a smart Monte Carlo approximation, to get accurate ways of approximating underlying density matrices. Okay? And this preparation stage hopefully convinces you that we now have a Monte Carlo approximation procedure that in principle allows us to use near-term quantum computers to do the sampling. We have still very simple, structured, classical descriptions after the sampling stage, and if we average enough of them, we get accurate approximations of the underlying density matrix. The question now is, how many samples do we need? This is something I haven't talked about yet, but in Monte Carlo approximations, I always said if you do empirical averages often enough, you converge to the actual expectation value. And you can use techniques from probability theory to actually rigorously see when this convergence happens. And fortunately, it often happens much quicker than what you might think when you think about exponentially large and complicated objects. And in order to look at that, let us just quickly remind us what our Monte Carlo approximations, these classical shadows, look like is approximations, and it's tensor products of single qubit states. It's not quite states, but it's the post-measurement state we observed in a randomized measurement. And then we counterbalance the depolarizing effect by inverting a depolarizing channel that gives us something that looks like this on the right-hand side. And we obtain each of these outcomes with a probability that depends on the underlying state, like this. Okay? And now the question is, how many of these Monte Carlo samples do I need to approximate a certain property? Things that I'm interested in, like Hamiltonian terms in a VQE approximation. That's what we started with after all, right? And so here is a proposition which is actually very simple to prove. I will prove now on the whiteboard a simpler, somewhat weaker variant of that, that tells you that convergence of this type of Monte Carlo approximation actually happens quicker than you might think. And to set things up, let us fix an observable, a target function, like a term in the Hamiltonian, and let us assume that the weight of this observable is somewhat small, it's smaller than W. The weight is the number of qubits on which this observable acts non-trivially. So if W equals 2 would allow me to get all the Heisenberg Hamiltonian terms. Okay, X tensor identity everywhere else would be a weight 2 term. And we also fix a number of Monte Carlo samples M. This is the number we're actually interested in. And we set up the Monte Carlo approximation precisely as I tried to convey it. We empirically average, we get an approximation of the underlying state by empirically averaging Monte Carlo samples of this form, classical shadows. And because of linearity of the trace, I actually never have to build, if I want to just approximate an observable, I never have to build the big matrix. I can just get a Monte Carlo sample, which is a simple object, compute the expectation value for this Monte Carlo sample, and then average many of them to get an approximation of the true underlying expectation value. This is very good for numerics. Never have to build big matrices. But what we are out here now is the following statement, which tells you that this type of Monte Carlo approximation with M samples deviates, the probability that this estimator deviates by more than epsilon, our tolerance, from the actual true expectation value of the underlying quantum state. And what this tells you is that the probability of deviation is exponentially small in M. And this is something that you intuitively expect if you do Monte Carlo sampling, because if I toss coins very, very often, then I converge exponentially quickly to the true underlying expectation value, right? Maybe you've heard about that. This is the very same principle, but now for Monte Carlo sampling with quantum states. And we have to be a bit careful. There's like an epsilon squared dependence and a dependence.
So there's a question from Maries Ossols.
Yes.
So she's saying, they're saying, I don't know, 3 to the n operators don't seem to be enough to express any n qubit density matrix. You would need 4 to the n. Is that not a problem, or is the point that we are not trying to capture the state fully?
No, Maris, that's an excellent question. But remember that for each single qubit state, we actually have 6 options. And so the total number of potential Monte Carlo samples is 6 to the n. And this is enough to cover all the directions and all the dimensions of quantum state space, because quantum state space is 4 to the n dimensional. This is precisely one of the reasons why we go to all 3 Pauli basis measurements, because 2 of them wouldn't be enough, then kind of Marie's argument would hold. But here we do exactly enough, a bit more actually, in each qubit to get it right. Okay, so let's just prove this, right? It's not that difficult. That's the cool thing about elementary Monte Carlo approximations. You can use elementary probability theory to get exponential concentration bounds like this. And I'm not going to prove this proposition that I actually put on the whiteboard because it requires slightly more involved tools, but really just slightly. I just want to give a simpler example. And so the proof I want to do is I assume that my observable, to keep life simple, is a tensor product of Pauli matrices. And because it's weight W, the first W expansion coefficients are non-trivial Pauli matrices, and then everything else is the identity matrix. The proof would be exactly equivalent if my observable would be supported on other systems, but it's just easiest notationally to just look at the first W qubits. Otherwise, notation gets a bit overburdened, right? And now what do we have to do? We have an approximation, a Monte Carlo approximation, that is a sum over m independent Monte Carlo samples, and each Monte Carlo sample looks like this. It's the trace of this localized observable times the classical shadows, the Monte Carlo approximations, and there's m of them. But once I take the trace, this is really a sum of random numbers. There's no random matrices involved anymore. Rm, and Rm is just trace O rho hat m. This is just to notationally underline that we are really only thinking about random numbers here. The fact that the underlying approximation is a matrix was absorbed by taking the observable. And now we can really think about convergence of random numbers. And because of the computations we did on the last slide, we also know that the expectation value of these random numbers is the same by linearity as the expectation value of the original Monte Carlo sample. And we constructed the Monte Carlo sample precisely in a way that this is the actual density matrix. So this is trace O rho, which is good news because we get the right expectation value. Our Monte Carlo sampling zooms in on the right target. Now the question is, how many samples do we need? And now we are really in a regime where it's really just about coin tossing. We are interested in the expectation value of a single random variable, and we approximate it by drawing samples, tossing coins, recording the outcomes, and averaging them to get an idea of the actual approximation. And there's simple tail bounds, like Hoeffding's inequality, that tell you that such coin tosses converge exponentially quickly to the actual true expectation value. This is very close to the proof, to the proposition that I stated. And the only thing that matters is the actual size of the random variables. Are they like plus 10,000 and minus 10,000, or are they plus 1 and minus 1? If they can be large, then convergence happens less rapidly. But here, what is the size of these random numbers? Well, that's the size of trace O rho hat, absolute value. And now we can use the fact that we assume that our observable is localized. Because remember, our rho hats are tensor products of single qubit objects. And each of these single qubit objects is trace 1. And so I can just like zoom in onto the first W coefficients and forget the entire rest. This is equal to trace W1, 3, S1, S1 minus identity matrix. And then I actually get a product from I equals 1 to W only over the first W qubits, but the rest doesn't feature at all. Because our observable is localized, I don't have to care about the remaining n minus W qubits at all. I just trace them out. And now these guys here, they are eigenvectors of Pauli matrices. And now we want to ask, what is the expectation value of eigenvalues of Pauli matrices for another Pauli matrix? This might be the same Pauli matrix or a different one. If you think a bit about that, there's only 3 options. This expectation value is 0 if this is an eigenvector of a Pauli matrix that is different from Wi, because then it's like the expectation value of plus minus 1 with respect to computational z is 0. And if it's the same, what you get is actually 3. Because if this is an eigenvector of a Pauli matrix Wi minus the identity here, that's still important. No, we can actually remove that because the Pauli matrix Wi is traceless. So if this is an eigenvalue of the same Pauli matrix, we will get 3 because it's an eigenvector of the Pauli matrix. So this is always smaller or equal than 3, and this is possible for each qubit. So it can only be as large as 3 to the power of W, exponentially in the weight, not the number of qubits. And this is all we need. The rest follows from Hoeffding's inequality. Because this tells us that Rm is in an interval that is as most minus 3 to the W, 3 to the W, and now the probability of the empirical average being very far away from the true expectation value, which is the thing we care about, greater or equal than epsilon, is smaller or equal than 2 to the e to the minus m over epsilon squared. And then here we have 3 to the w minus 3 to the w squared. That's what Hoeffding tells you. It gives you an additional suppression coefficient that is quadratic in the size of your interval. And if you do simplify this exponent, you get minus 2 to the minus m epsilon squared over 9 to the w. Sorry, 2 times e to the minus this. And this is almost the proposition I advertised with a slightly worse dependence on the weight. Because here I have 4 to the w, and you get that by using a somewhat more sophisticated argument than Hoeffding's inequality to analyze the concentration of essentially a random variable, an empirical average of coins, towards the expectation value. But I hope you see where this comes from. And it's really one of the most elementary strategies that you learn in probability theory. Empirical averages, and they converge exponentially quickly to the true expectation value with a small twist, namely that the rate of convergence depends on the locality of the observable and is completely independent of the global system size. This is very good news. Because it tells us that if you want to estimate a single weight W observable, then the number of Monte Carlo samples we need scales exponentially in W and is completely independent of the number of qubits, right? And if you are here with exponential concentration, we actually can say, well, the proposition here tells us that for an arbitrary fixed observable with weight W, the probability of being further away than epsilon is exponentially small in the number of samples m, right? This is exponential concentration. And now we can ask ourselves, what happens if we are more greedy? If we don't want to only approximate one observable, but many of them at the same time. Let's say we want to approximate L, where this is a potentially large number of these weight W observables with the same Monte Carlo approximations. Let's be greedy. Let's use the same Monte Carlo sampling to approximate in parallel many different objects. This is one of the advantages you can do. Then how many samples do we expect to need here? Well, we only pay an extra logarithmic factor in the number of observables we want to predict compared to the original proposition. And this ensures us that with high probability, we get all of them correct simultaneously. And correct means we get an epsilon approximation to all of them. And the proof is now really easy. It's based on a union-bound argument. Like, what has to happen in order for this advertised event to be wrong? That means there has to be at least one observable where the approximation error we make is larger than epsilon, right? And what is the probability of this happening? Well, it's a probability of a union of possibilities. It's possible that the first one is wrong, it's possible the second one is wrong, the third one is wrong, and so on. And the union bound is a very simple tool from probability theory that tells you that the probability of a union is always upper bounded by the sum of the individual probabilities. So union bound allows us to start with this maximum deviation and upper bound it by a sum of individual deviations. And now we just use proposition, right? Because the proposition tells us that the probability for each of the observables, that the deviation is larger than epsilon, is exponentially small in m. And how large do we have to choose m to counterbalance the fact that we now, with the union bound, have a sum over L probabilities? Well, that's the logarithm of L, right? Because it enters in the exponent. Okay, and so the proposition actually easily extends to a theorem that tells us we don't only have to estimate a single property with our Monte Carlo samples. We can do as many as we want, as long as we pay a logarithmic overhead. And it's really just a union bound argument combined with exponential concentration for Monte Carlo averaging. This is where Monte Carlo helps. And this is also where the logarithmic factor came from on the second slide when we introduced and discussed the Heisenberg Hamiltonian. There's L terms, all of them weigh 2. Just use this theorem. Yes?
Yeah, that should work. Very good question. So, the L observables, you comment on, there was a paper about using methods to sort of Monte Carlo sampling where you condition the next observable on previous observables. Can you comment on what happens in kind of arguments when the L weight value of observables is one is conditioned on the last? Seems that they need to be also
Sorry, I had difficulties understanding that from the audio.
should I turn that off? Let's talk about it. Can you hear me now?
I think so, yes.
Okay. So can you comment on what happens when the L weight value observables are not necessarily independent of each other? So for example, some people talk about doing sort of Monte Carlo style simulations by using samples.
Yes, thank you. Now I understand you. This is a brilliant question. Like for now, let me just state the obvious. This theorem is still true, right? It doesn't care about dependencies because of the union bound. But what could happen is that the approximation probabilities can become correlated, right? There's like a good thing and a bad thing that can happen. Maybe if all the observables are very similar and I'm unlucky with my Monte Carlo sample, then like one sample might destroy or like distort all of them simultaneously. But the probability for this happening is still small because the theorem applies. And then there's the other thing that is maybe better and more optimistic, is that if we actually have structure in the observables, we could try to temper with our Monte Carlo sampling techniques to kind of continue to use what we already learned to become more efficient in predicting future events by doing an adaptive procedure, right? On a very high level, this is what you could do. Are you with me, or am I not answering your question?
I'm not sure, just sort of saying. So maybe this is
Yes, I will talk about adaptive measurement strategies, which are maybe a bit closer to what you're suggesting at the end of the talk. And we will see that there's fundamental lower bounds that tell you that in the worst case, they don't help. And the situation will be different. Yes.
And then but then you're not choosing your L weight of the observables independently. You choose one, you find it like
Yes.
Your next one.
Yeah, sorry. In this case, the theorem breaks down. What I intrinsically have to assume, thank you, now I'm with you. Like what is important here is that the observables might be unknown, but they have to be fixed before I do the sampling. Because otherwise, once I've done the sampling, an adversary could come and present me with an observable that depends, kind of like uses the fact that my data is skewed in a certain direction, and that will screw me over. Is that closer to what you wanted to say? Thank you. Exactly. Like here, it's important that we first assume that the L observables are fixed. We don't need to know them yet, but they are fixed and don't depend on the data we've actually taken, because otherwise weird things can happen. Thank you very much. This was a very important comment, and sorry that it took me so long to follow up on it. Okay, but this is a theorem that holds as long as the observables we're interested in are uncorrelated with the Monte Carlo sampling. This is the one assumption you need. And then you have this. And this actually checks a lot of boxes, at least in my opinion. Yes?
So there are two questions from the chat. So the first is, both of them are by Ronald Wolf.
Yes.
The first question is, can rho hat have negative eigenvalues?
Yes. Yes, it has by construction. Every single qubit is a tensor product of 3 times the pure state minus the identity. Every single qubit has a negative eigenvalue.
And also he says that the largest eigenvalue would be 2 to the n. It's worth emphasizing that rho hat is very far from a density matrix.
Yes, that's also true. Thank you, Ronald. These rho hats are really only approximate the actual density matrix in expectation. They have many negative eigenvalues. Like for each qubit, there's 1 negative eigenvalue, and the operator, the largest eigenvalue is indeed exponentially large. So every single shot is very far away, but because we average many of them and reduce to properties, this actually doesn't matter. And we can just do Monte Carlo sampling. Thank you very much. Now I'm almost done. I just want to emphasize that this theorem is actually kind of checks a couple of NISQ-worthy boxes, I think. Kind of like the reconstruction here is independent of the number of qubits. That's nice. It's logarithmic in the number of things we want to predict. That's also nice. This is what Monte Carlo sampling gives us. What's not so nice is that the scaling is exponential in the support, in the weights of the observables we care about. But this is also kind of like not so surprising if we sample each Pauli matrix uniformly at random and we want to estimate a Pauli matrix, then the probability of hitting it, of being compatible with that in our Monte Carlo sampling is exponentially small in the weight, right? It's just a general property. But I think what's really important is that the sampling process is delegated to a quantum computer, so we never have to build density matrices, and it's comparatively cheap. All you need to have in order to execute it is a way to prepare your state, and then you have to be able to do simple single qubit rotations into X and Y bases, respectively. And the storage is also easy, because each of the Monte Carlo approximations is a tensor product, and each individual factor depends on 6 possibilities, and so I can only always store a list of these 6 possibilities of length n, and I can always do that with at most 3n bits. So storage is also cheap. And finally, efficient processing is also, post-processing is also possible because of this nice tensor product structure. As long as the observables we care about also have some tensor product structure or are only restricted to subsystems, I can always forget about everything outside the subsystem and do my post-processing only on the relevant subspaces, regardless where they are. Yes? Hi.
Can you comment at all on the noise robustness of the spectrum?
I will do that in the second part. Can we do that?
Oh,
I have an entire chapter in the second part delegated to noise robustness. Thank you very much for giving me the chance to advertise that. Is there another question? Yes?
I have one. Is the story basically the same if you consider arbitrary single qubit rotation?
Yes. So he was asking if the story would basically be the same if I do arbitrary single qubit rotations. And yes, very much so. Actually, in my first derivation of the depolarizing bias of the individual single qubit factors actually alluded to that fact. I pointed out that if I do these octahedral measurements, it's the same as going over the full unitary group. So actually, the story is very, very similar. The only thing is if you do continuous single qubit rotations, you need to be able to implement them on quantum hardware, which you can take as a given. Storage and post-processing can become nastier, though. So we did numerical experiments for like large system sizes with 200 qubits, and their floating point accuracy starts to matter. And it's actually a distinct advantage that these are almost discrete options for each single qubit, where you can use kind of like, let's say, integers, products of integers to approximate Pauli expectation values. So that's part of the efficient storage and post-processing. It's actually an advantage of having this very, very rich structure. And you have to be a bit careful, as the comment from the other lecture hall correctly pointed out. The measurement procedure is completely decoupled from the things we actually care about. We just do randomized measurements, and then afterwards, we go back and maybe ask our advisors or experimental friends what you actually want to know, and then you average. Of course, this has a caveat, as we discussed earlier. There mustn't be any correlations between the data I've taken and the observables I want to predict, because then I would be in trouble. But as long as this is not the case, as long as the observables are independent of the data that I've taken, this is fine. And this also allows you to change your mind halfway through experiments or even after the experiment is over, because you've decoupled the experimental data acquisition process from the predictions. And you can really summarize that as measure now, ask questions later. And I think this is very beneficial in case if you maybe have a capricious advisor or something. Just do these, and then you're basically ready, and in the future, you can wait for new questions and reuse the data again. And with that, I'm actually at the end of the first part of the lecture. I want to thank you very much, and I just want to quickly point out that we've now actually filled in the gaps that I kind of like left on the second slide, because we now really proved and understood why single qubit randomized measurements are very good at predicting very many low weight observables, like it was in the case with the Heisenberg Hamiltonian, right? There I pointed out that the randomized measurement method scales logarithmically in the number of terms. This is what Monte Carlo sampling gives you. And if you're interested in an actual plot, here's a plot from an actual VQE experiment, a beautiful one that was taken by the Innsbruck group in 2019, where they used VQE to simulate or approximate low energy eigenstates of an interesting quantum field theory. And they used VQE for that. And in order to get low energy eigenstates, and not just the lowest energy eigenstate, they looked not at the Hamiltonian itself, but the variance of the Hamiltonian. And this is a nice trick, because the variance of Hamiltonian vanishes exactly if the state we're at is an eigenstate, at least if the state is pure. And if you minimize the variance of Hamiltonian, you can actually get an idea of what the low energy eigenstates look like. But this turns a two-weight 2 operator, Hamiltonian, into a weight 4 operator, because I need to square it. And so the question they had is, how do I efficiently approximate a quadratic sum over 4 local operators? And this is a prime application of the randomized measurements we considered, because the theorems we derived tell us that the number of samples scales exponentially in the locality, 4 in this case. That's not that scary yet, and logarithmically in the number of terms. And on the right-hand side, you can actually see what that means. In a log-log plot, the number of measurements rise only there's like only a small incline if we increase system size, because it's a logarithmic dependence. Whereas if we directly measured all of these observables, the increase in measurement cost in the number of Monte Carlo samples we need would be much less favorable. And with that, I think we're ready for the break, right? Thank you very much for your attention.
Hi, everyone. Welcome back. Right. Thank you so much. So I think we're ready to resume the session. And yeah, let me not take too much of your time. Richard, Küng. Thank you.
Thank you very much. Thank you very much for coming back. It actually means a lot that you are still staying with me for the second half of the tutorial. I take this as a good sign. I also want to thank all of you for being so attentive, and I'm also really happy about the questions I got during the talk, because I think they helped me clarify a lot of important points and made the overall presentation clearer. So please continue to do that. I think it's great. And now, in the first half, I really tried to be rather slow-paced and really go a bit into details and give you an idea of how Monte Carlo sampling with quantum devices could work. And what we actually ended up with is, in my opinion, surprisingly strong result, convergence guarantees for Monte Carlo sampling with local, and local means single qubit randomized measurements. And in the first lecture, we showed that such a measurement setup kind of like allows us to predict many low-weight observables at the same time extremely efficiently. And now in the second part of the lecture, I want to use this as a starting point and being less detailed, I want to go on a higher level overview of how you can extend these ideas if there's other variants, and what other interesting problems are connected to this type of quantum state approximation based on Monte Carlo sampling. We will cover more ground. I will be more high level, but I still am happy to take questions. And so to kick it off, let's now really jump to a higher level. And I want to point out that on a high diagrammatic level, there's a nice symmetry between the measurement process we did and the type of Monte Carlo approximations we ended up with. So for these randomized single qubit measurements, the sampling process is prepare the unknown state, apply random single qubit unitaries, Hadamard or S times Hadamard or nothing, and then perform a computational basis measurement. And then based on the measurement outcome and the unitaries we did, the Monte Carlo estimator almost looks the same as the post-measurement state. So it decomposes nicely into tensor products because we have a computational basis measurements here, and we will see the same unitaries on the right-hand side, but with an adjoint that are notationally suppressed. The one caveat was that this wasn't quite enough, because if we average things that look like this, then we get a depolarized variant of the original state. And in order to compensate for that, we have to invert these depolarizing channels. And that means that this is actually not the correct answer, but we have to apply an inverse depolarizing channel to each of these single qubit operators. And this introduces negative eigenvalues and exponentially largest eigenvalues. As Ronald pointed out in the first half, this is what makes the estimators unphysical. But for estimation purposes, this is really not a problem. And I want to emphasize a very nice symmetry between the sampling process and what the actual Monte Carlo samples look like, at least for randomized single qubit measurements. And then remember, I try to emphasize that this is a very tractable quantum sampling problem. Every near-term quantum computer should be able to execute those, because it's really just random single qubit rotations at the end. It's cheap in classical storage. Here we see why. It decomposes really nicely into tensor products of simple things. It has efficient post-processing because of the same reason. We can always just forget parts of the density matrix we don't care about right now for our current estimation task. And the theorem we derived told us that it is provably good for estimating many localized properties. That was the main result from the first half, right? But this is just one example, right? There's many ways of thinking how we could do Monte Carlo sampling with quantum devices. Here's arguably one of the easiest ones because we only used single qubit rotations, and this gave us a very simple sampling process and a very simple Monte Carlo approximation. But this is certainly not the only way we could do it. Another way, but it is good for localized measurements, and I think I will talk about this figure later. It just shows that you can actually accurately reproduce localized properties, in this case 2-point correlators, and the runtime is much more efficient than back then state-of-the-art methods were, simply because Monte Carlo sampling is designed to be numerically very efficient. But now, the take-home message here is really single qubit measurements give us tensor product estimators for local properties. And if you just look at the pictures, you probably see why. Single qubit, tensor product, and then we can get localized information very well, but global information will be difficult to obtain. But we could just change our Monte Carlo sampling procedure, right? We could also think about preparing our quantum state, and instead of doing single qubit rotations, do something more sophisticated, maybe a deep quantum circuit that scrambles information over all subsystems. Think of a Clifford unitary or a 2-design unitary so that information actually scrambles. And the hope is that these scrambling unitaries actually allow us to resolve global properties, because those are precisely the things that the single qubit measurements from the previous slide struggled with, right? Think about fidelities with pure states or something. They can be highly non-local, and then the single qubit measurements wouldn't be very good. Maybe intuition tells maybe we could do these scrambling larger unitaries to get a different Monte Carlo approximation method that is better for scrambled, for global properties. And the answer turns out that this is actually true. And again, just based on Monte Carlo approximations, if this is our Monte Carlo approximation process, sample a scrambling unitary at random, perform a computational basis measurement, that it seems reasonable or to make as our Monte Carlo sample approximation kind of like the post-measurement state again. But again, we probably have to correct it, right? Because this might not yield us the actual density matrix in expectation. And it turns out that for these global scrambling unitaries, the correction is even easier than in the single qubit case, because if our U's are chosen from an example that scrambles information, then you scramble and you take the average, then you effectively average over quadratic properties of a scrambling unitary. Scrambling unitary is roughly 2 design, and you can again use the 2 design property that we used on a single qubit level on the whiteboard to compute the expected outcome for the global system. And our outcome was a depolarization. And the same is true for these global scrambling unitaries. The bias you get is a single depolarizing channel that acts on the entire global 2 to the n dimensional system and pushes it closer to the identity matrix. And you can again undo that in classical post-processing. You just multiply it with an exponentially large number to counterbalance the depolarization probability and subtract the identity because it's the fixed point of the depolarizing channel. But the same story is true. And this was also found out by Robert, myself, and John. But at the same time, similar ideas were also provided by Josh Morris and Borivoje Darkic in Vienna. So this was around back at the time. And if we just look at that, how cool is this? How useful is it? Like the first thing we have to begrudgingly confess is that deep scrambling unitaries are not near term, right? In order to get a scrambling unitary, the depth of the circuit or the size of the circuit has to be like at least linear or quadratic in the number of qubits. And these circuits are simply too deep for our NISQ term devices. So it's kind of not on the horizon yet. It's also not clear if we can efficiently store the Monte Carlo approximations anymore, because in the worst case, it would require us to store a representation of a scrambling unitary, which is not necessarily easy. It is easy, however, if we use Clifford unitaries for scrambling, because Clifford unitaries are easy to store using the Gottesman-Nil theorem. And the post-processing cost also depends. If you do Clifford scrambling unitaries, then you don't only have efficient storage, but you can also efficiently compute properties like fidelities with other stabilizer states, because you always stay within the Gottesman-Nil framework, where you can compute these exponentially large things efficiently. But for more general target functions, post-processing might become exponentially costly simply because we've scrambled over everything and we're looking at highly non-localized information. That's probably also not so surprising. And you can actually use the ideas and the mathematical methods we discussed in the first part of the lecture to also come up with a probabilistic reconstruction guarantee, a convergence guarantee for Monte Carlo sampling in this picture, where the number of measurements depend on the Hilbert-Schmidt norm of the observables. And this kind of tells you that if you're interested in estimating, for example, fidelities with pure states, then this is very cheap, because a pure state has Hilbert-Schmidt norm 1. Yes?
In the local figure case, the big L was the number of
Yes.
factor, but here was the big L.
Thank you for pointing that out. The big L is still, he asked what does L stand for in this formula? It's the same thing. Here we envision that we are still interested in predicting L many different properties. The question is now, like, what are the good properties and what are bad properties? And so here, for example, you could think about trying to predict L different fidelities with L different target states. And then this result would tell you that the number of measurements you need, these global scrambled measurements, is actually completely independent of the number of qubits, simply because the trace of a state squared is 1. And it's still logarithmic in the number of parameters. But I hope that you see the high-level picture. Globally scrambling measurement, globally scrambling Monte Carlo approximation, good for predicting global properties. It's a very nice, consistent story, I think. And one application, it's not so clear because it's not near term, is, for example, to do entanglement detection. Because in entanglement theory, maybe you've learned that somewhere, there's entanglement witnesses. and every entangled state has a witness. This is typically a linear function, maybe the trace inner product or the fidelity with another entangled state. And if you can show that this is beyond a certain threshold, you have shown that the state you've prepared must be entangled. So entanglement witnesses are, in the easiest case, linear functions that are typically fidelities with pure states. And if you want to estimate many possible witnesses, because it's not clear, it's very difficult to find the right witness for a given state. So a good way is to check as many of them as you can. And this is precisely a regime where these global scrambling unitaries can help, because this theorem tells you that you can predict exponentially many entanglement witnesses with only polynomially many samples. And this is kind of illustrated in this plot, where if you would naively measure entanglement witnesses one after the other, again, it's fidelities with entangled pure states in the easiest case, it's much more costly than doing these global scrambling Monte Carlo approximations and getting many more of them at the same time. But the take-home message is really, we can adjust the Monte Carlo sampling scheme, and there are symmetries. Yes?
So there's a question from Logan Qian. And the question is the dependence on the Hilbert-Schmidt norm inherent? Is there an example showing that estimating a certain observable requires exponential samples for an observable with large Hilbert-Schmidt norm?
That's a very good question. In principle, not here yet, but we will later talk about fundamental lower bounds that will assert that if that we can find observables that have exponentially large Hilbert-Schmidt norm, and this would imply exponentially high Monte Carlo sampling cost, but there's a fundamental lower bound that will tell us that this is unavoidable. Any other procedure also has to have this feature, and the counterexamples we use actually are precisely observables with exponentially large Hilbert-Schmidt norm. So yes, that was a very good question, and yes?
The single qubit Cliffords are a subgroup of the global Cliffords.
Yes.
Does that imply any relationship between what these procedures are good at predicting?
This is a very interesting question. What he pointed out, rightfully, is that the single qubit Cliffords are a subgroup of the global Cliffords, and so you can ask yourself if there's an obvious relation. And I think it's not so clear directly on the group level, because the subgroup is just much, much smaller than the full group, but at least the proof technique is exactly the same. Kind of like if you carefully paid attention in the first half, where I did the single qubit averages, then the same story applies here, and it's again a depolarizing channel. And more sophisticated results are possible, but I think I don't want to go into that detail now. I hope I've answered your question. Okay, but the take-home message is really scrambling measurement, scrambled estimators, which is good for predicting global properties, but it might be expensive on our classical hardware. And now you can ask yourself, well, following up on his point, the local single qubit measurements were kind of an extreme version of a random circuit where the depth is 0 or 1. Like single qubit unitaries in tensor product have depth 1, right? And the scrambling unitaries are another extreme where the depth is so large that the information is fully scrambled. What about the intermediate regime? What about random circuits that are somewhat short depth? Let's say depth 1, 2, 3, 4, 5 or something, so that it is still near-term feasible. And if you actually analyze this case, you will see there's again a symmetry. If you apply a short depth random circuit in your Monte Carlo sampling process, then your Monte Carlo samples themselves will also feature the same random circuit that you chose, but in reverse. And you again can compute, kind of like this will again introduce some bias, some depolarization or whatever it is, that distorts your true Monte Carlo average, but you can undo that with an inversion map. And now this setup with short depth random circuits allows you to interpolate between the two extremes I talked about. And this was a really cool paper by some young researchers in San Diego who pointed that out and actually rigorously analyzed that Monte Carlo sampling with short depth circuit actually really interpolates between the two extremes we've seen. They actually use tensor network techniques to kind of make storage and post-processing possible. Like now you can think that like if I want to store a state like this, the storage cost will depend on depth, the size of the short depth random circuits. But if it's short enough, I can use tensor network techniques to make this possible. And the same is true for classical post-processing. And if the circuit's even better, if they are not too large, then they are also near-term feasible. And what they actually showed, and I think this is very beautiful, is that these near-term, kind of like these short depth random circuits, really interpolate between local and global, which if you just look at the pictures is what they should do, right? There's just one bottleneck. If we use short depth random circuits here, then they don't necessarily form a group. And so you can't use these nice averaging tricks that I used on the whiteboard earlier, and it's actually very difficult to actually compute the bias map in the average. So this is the one thing where this approach is not yet efficient. They have to work very hard to get an idea, if I have short depth random circuits of size 5, what does the average bias channel look like, and how can I undo it? Mainly because they can't use very nice group properties that helped us under the hood to get these depolarization channels. But I think there's still room for improvement, and that's a really cool example. And here, this is a plot taken from their paper where they ask the question, suppose I want to estimate the fidelity with a GHZ state. And a GHZ state is something that's very non-local. And so fidelity with a GHZ state is an example where these local single qubit randomized measurements are very bad. The weight of the fidelity as an observable is 2 to the n for a GHZ state. It's n, sorry, so we have exponential dependence in n. But it is a pure state, and so the Hilbert-Schmidt norm squared would be squared, and so it would be very easy for these scrambling randomized measurements. And here you see essentially how the cost of measurement, how many measurements do I need, decreases as the depth of the random circuit increases. So on the x-axis, you see the depth of the random circuits, and on the y-axis, the variance of the estimator is a good measure. You want this to get small in order to be accurate. And you can really see that already very short depth circuits make a huge difference for these types of non-local observables. So take-home message, again, very symmetric. If we take short depth circuits or depth L circuits more generally, then we get partially scrambled estimators that interpolate between these very short depth localized measurements and this very long depth global scrambling measurements. And you reap advantages very quickly, potentially. And I think this is an interesting problem for further study in the next couple of years, how we can use these short depth random circuits to just get the measurement cost down for some observables that are not exactly localized. Okay? And really for you, this is just an invitation. If you have an application, if you want to estimate certain properties, then you can use these symmetries and this high-level intuition to come up with your own Monte Carlo sampling method, where the structure or symmetry is somewhat geared towards the applications you want to make. And chances are that the only difficult thing will be to compute these inverse channels. But you can still do that, and I think there's a lot of potential for further specifications for applications. I only gave you the one extreme case of no depth, deep, and then continuous interpolation between, but I think many more things are actually possible. Okay, and with that, I want to go to another very important question, especially when I use near-term quantum computers as a motivation. We have to think about noise and noise corruption in our measurement process. And so I think that should also deserves an entire chapter. And if you use these localized or global random unitaries and the intuition that the gentleman in the audience with the great question gave, namely that both the local measurements and the global ones actually have a group structure. The easiest case is to use Cliffords. Then something interesting happens if you look at these high-level representations. Remember, regardless whether this is global or local, as long as this is a group, we do a random element of the group here in the sampling process, and then we undo the same random element in the post-processing. And we have to apply an inverse channel, but the inverse channel depends on the average over the group, and so it also commutes with the group. And if you appreciate that, you will see that the entire estimation process is actually invariant after applying an other unitary from the same group. If my procedure is I sample a random Clifford element, and my post-processing element depends on the same random Clifford element, if somebody of you comes and say, Richard, do the same but apply this particular Clifford unitary before, then my strategy doesn't change, because I sample uniformly from the group, and so I can just kind of in principle apply another group term there. And this is something that Steve Lamere and his group actually discovered, that the randomized measurement procedure, as I explained it in terms of Monte Carlo sampling, is twirl invariant under the actual group that we use to generate the randomized measurements if there's a group structure present. And invariance like this is very closely related to the ideas that you maybe know from randomized benchmarking, right? There you use exactly invariance properties like this to implicitly average over the noise effects and depolarize them, or at least turn them into something simpler. And you can do the same here by using, first adjusting the randomized measurement process with a fixed unitary, at least virtually, and then adjust the estimator you do accordingly. And this allows you to, at least hypothetically, you never do it actually, twirl over the noise effects that actually plague your measurement process. And the two examples I gave, the single local and global Clifford groups, they're actually very well understood in randomized benchmarking, right? We know that if we have a global Clifford invariance, then we can twirl over the noise and we'll get a single global depolarizing channel with a single error parameter that, if we know that, we know what the noise actually effectively looks like. This is what the first papers in randomized benchmarking promised. And more recently, we understand the same story also for local Cliffords. They are not big enough to depolarize, to turn every noise into a single depolarizing channel, but they will still turn the noise into an effective poly channel, which can then be learned. And what Steve Lamere's group pointed out, and this was really beautiful, is they came up with an RB-inspired protocol to actually learn these effective noise channels prior to the Monte Carlo sampling. You can, if you have access to a single pure state that you know, then you can actually use a pre-processing, a calibration stage of a very similar algorithm to learn the effective noise channel. And once you've done that, you can adjust the inversion map in the Monte Carlo estimation to completely counterbalance for these noise effects. As an example, if you have the global Clifford group, then I told you earlier that you have to also apply on the right-hand side to the Monte Carlo samplings the inverse of a global depolarizing channel. Now suppose that your measurements were noisy, then these twirling effects tell you it will act as an effective additional depolarizing channel, but then I just take this into account in my averaging, and the actual average will be a depolarizing channel with a larger parameter. And if I know this parameter, I can perfectly counterbalance that. And this actually gives you a calibration stage where you can use the randomness in the measurements to twirl away noise and do error mitigation and even error correction. And they worked very hard actually to show that everything is somewhat tractable, and the number of measurements you need and the general cost scales exactly how you would imagine it. And here's actually a plot I quickly want to show. Here they did an experiment similar to the one I mentioned before with local single qubit noise, with local single qubit randomized measurements. And this is just the 2-point correlators of a transverse field Ising model. But now the measurements have a 5% bit flip noise. And what you can see here is that very systematically, the red part would be the standard shadows without error correction. They really just depolarize. They really just make the values a bit smaller. And their method, the blue points, actually find that dampening parameter and actually undo it. And so the blue points here look virtually identical to the plot I had before, where we looked at noiseless measurements. Yes?
So there's another question from the online chat. This is by Arthur Dominguez. Sorry, I may have pronounced it wrong. The question is, what are the caveats of not measuring all qubits but inferring information about the qubits given a smaller set of measurements realized? And he says, my question is inspired by the Baden Plateau issues the Baden Plateau's issue and the local cost function resolution. I'm rather new to the area. Sorry, this question seems kind of silly.
Okay, I will. Thank you. That is a very good question. I would like to delay it though, because I will later talk quickly about barren plateaus myself. And I think like maintaining, I don't want to go a bit too much about like post-election and something like that, but remember that you can use these classical randomized measurements to predict many local properties at the same time. And I think this is powerful, but I will talk more about this later. I mean, here, this is, I think, really beautiful because the randomized measurement procedure itself acts like a randomized measurement protocol, so you never really have to do it. And you can actually learn error effects, effective error effects, and undo them and get the corrections you need in order to still do Monte Carlo sampling as if you had a perfectly working quantum computer. And this is, I think, really a game changer if I want to claim that these things are useful for NISC devices. And it's a game changer thanks to Steve Flamier's group, and also Ko and Grewal had similar ideas at the same time. I don't have slide space here, but the converse direction also works. You can use these randomized measurements ideas to augment existing randomized benchmarking protocols by simply using your measurement data at the end, not to simply estimate kind of damping factors of depolarizing channels, but really use the full data to estimate many calibration parameters at the same time. And this is something that Jens Eisart's group has pointed out, and this is also very interesting. There's just much more information in your data than you would use to do a normal randomized benchmarking protocol. And these randomized measurements are one way to harness it. Okay, now, next step. So far, we've only talked about approximating linear functions, like observables and things like that. Yeah, there's a question.
Yeah, I have a question about the previous slide. So, are there some assumptions on the noise?
Yes, thank you. He asked, and thank you for this question, it's very important. Are there assumptions on the noise process? And the answer is yes. They use the normal assumptions from randomized benchmarking. In the concrete case, gate-independent, not non-Markovian noise. So this is what they need because they really use an RB-inspired protocol to learn effective noise channel. But this is very important. Of course, you can cook up noise models that temper and destroy this type of estimation.
One question here as well.
Yes?
Yeah, I'll just try and figure it out.
Sorry, again, I have difficulties understanding you.
Maybe I'll just leave my question until later. I can't get it later.
Can you maybe change lecture hall, actually? and then we do that later, okay? I'm sorry.
That was a very important question. I just was curious if you comment. So this is about the twirling unitary, twirling noise.
Yes.
And how do you, can you make comments on your guarantees? You talked about the last lecture with relation to readers, thinking of standards.
Yes, this paper, the Flamier paper, contains variants of statements that are exactly the same as the statements we derived in the first lecture, but they include this calibration stage. And they base it like kind of they have normal noise effects, like some average fidelities or something in there. And they tell you how the number of Monte Carlo samples must increase in the noise strength. Am I answering your question?
Yeah, I'm just concerned that maybe the real error is making a bit conservative and kind of very long.
Yes, but I think the number of measurements you need for the full procedure, if you have, let's say, some noise strength P, scales inverse quadratically in P or something. Maybe just look up the paper. It's actually very helpful. Thanks. Okay, thank you. This was, again, a very good question. I'm sorry that I always take a while to understand you in the other lecture hall, but I think it's worth it. So now, again, let me jump to the next section again. What about nonlinear functions? Like I motivated in the first part Monte Carlo sampling and said it's basically very efficient because if you estimate linear functions, you can always pull the average in or outside of the trace. And this allows you to do your average only for numbers if you're interested in a linear number, and you never have to construct the full matrices. Now, a valid question is this a fixed feature of linear functions, or can we do similar things for higher order functions, polynomials as well? Does Monte Carlo sampling for nonlinear functions work? And the short answer is yes. And a good instructive example to see how it could work is estimating the simplest nonlinear function I can think of, the purity of a density matrix. And this could now be the global purity, but it could also be the purity of a subsystem. And here's how you can actually estimate the purity. If I have m different Monte Carlo samples, remember that by assumption, each of these Monte Carlo samples comes from a different experimental run. And so the different Monte Carlo estimators are statistically independent because we do a different sampling process every time. This is an important feature of standard Monte Carlo methods. And if I know that my Monte Carlo estimators are independent, I can just make the following ansatz. In order to estimate a quadratic function in rho, I just approximate the quadratic function by the trace of one of my Monte Carlo samples with another one, a different one. That's important, because as long as the two are different, independence assures that the expectation value factorizes, and I'm ending up with a quadratic property, right? I'm ending up with the purity of rho itself. With this, I want to say you can use independence between the Monte Carlo samples to build nonlinear estimators that still have the right expectation value because independence assures that these expectations have to factorize. This is just the simplest example, where you also sum over all possible pairs of distinct Monte Carlo shadows to use them as much of your data as you can. And I hope nobody of you is surprised that this generalizes to higher order polynomials. And the first step is always rewrite your function, maybe as a polynomial, do an approximation if it's not one, and then rewrite the polynomial as a linear function on the tensor product. You can always do that. The purity is a linear function in the tensor product of two copies, for instance. And now I just pretend that this is a linear observable in a much larger state, namely the default tensor product of rho with itself. And how should I approximate it? Well, by tensor producting the different Monte Carlo estimators, and the only requirement I have is to never use the same estimator twice. Because then independence tells me that this is again a good unbiased estimator for the true tensor product. And to get as much convergence as I can, I should average over all possible combinations of distinct Monte Carlo approximations to squeeze as much out of my data as I can. And if you follow this procedure through, all the ideas from the first lecture extend to polynomial functions. And you can actually get rigorous error bounds. And I think it's quite interestingly that at least in the large sample regime, the number of measurements you need only scales polynomial in the degree. So although we use a trick to make the entire estimation process exponentially larger, if you use your data wisely, a property for few statistics estimators, which is the statistically correct term of these type of Monte Carlo approximations, tells you that the number of samples still only grows polynomially. And that means that you can do degree 2, 3, 4 polynomials without problem. I should mention, however, that the classical post-processing cost will become more difficult because you always have to find distinct pairs. And this can just become a numerical obstacle at some point, but not that much. And if you know how to approximate quadratic functions, maybe even in subsystems, you can start using them to do interesting physics, right? And I'm very happy to see Peter and John in the audience because this is a project that was a collaboration between Robert, John, and myself, and Peter Zoller's group with Andreas Elmo is also here. And what we used here is to use exactly these Monte Carlo approximation techniques to estimate certain quadratic and order 3 polynomials that tell us something about entanglement. For instance, maybe many of you will know that if your state is pure, then the subsystem Renyi entropies, which are essentially subsystem purities, tell you something about the entanglement. And if you know that your state is pure, looking at the purities is actually enough. The problem is, what if your state is not pure? The maximally mixed state, for instance, also has very high subsystem Renyi entropies. But what we found out in this paper is that you can compare the squared purity of a subsystem with a degree 3 polynomial that depends on the partial trace of the system And if the ratio between these two objects is larger than 1, then you're guaranteed to have a non-positive partial transpose, which implies mixed state entanglement. And here on the right-hand side, we actually did that on real experimental data that that Christian Rose's group did actually prior to that to analyze how the entanglement between a system here and a system a bit further away actually evolves in time when you apply a quantum quench to the entire system. And here you see this ratio as it behaves for different distances between the two systems. And suddenly you see some interesting physics here, because the light red curve just asks you how the entanglement, or like kind of the entanglement, if there's entanglement between sister qubits 1, 2, 3 and 4, 5, 6, so they're immediately adjacent. And you see that the entanglement factor quickly grows above 1. So adjacent systems quickly become entangled during a quantum quench. This is kind of something you would physically expect. And the other lines are further away. And there you can see that there's a burn-in period, that there's a certain time it takes to entangle the first part of the system with the last. Okay? And so I think there's like some interesting physics actually hiding here. And another take-home message is that here we really use this measure now, ask questions later principle, because this plot has error bars, which means that it's actually based on experimental data, but it's based on experimental data that Christian Rose's group used for a completely different experiment, right? We just asked them nicely, they gave it to us, and we reanalyzed it, we reused it to see these effects. And here, there's a second application that some people from IST Austria recently came up with. If you know how to predict subsystem purities, and you're interested in VQE, and you're afraid of barren plateaus, then you can use these, then you can, in principle, compute reduced Renyi entropies in each step of your VQE approximation to check whether we've reached a barren plateau or not. Because in the simplest case, a barren plateau is scrambling as a 2 design property. That means we have entanglement. That means all subsystem purities must be large. And this gives you one way of efficiently reusing the data within each VQE step to have an additional test process that flags for the possible presence of barren plateaus. And if you see them, you can counteract by either restarting the entire loop or making the parameters in the optimization smaller. And so this actually kind of helps you to look around within each VQE step, compute, approximate some simple quadratic functions to avoid running into these barren plateaus. So take-home message is, if you drink the Monte Carlo sampling Kool-Aid, then you're not restricted to linear functions. You can use the same ideas very, very simply with a couple of tensor product tricks to also approximate polynomial functions, which you could in principle then afterwards use to approximate analytic functions as well. So, okay, with that, I want to, yes?
Yeah, and just a technicality, but so the former slide, when dealing with polynomial functions, the terms in the sum are no longer independent, right? Can you explain why this isn't a problem intuitively, or whether we still have concentration though?
Thank you very much. He's asking if I actually do that, then there's no longer independence between the different samples, and you have to look at concentration. And this is exactly what this U-statistics framework by Höfting gives you. Höfting kind of like solved the problem for us for the normal case of estimating quadratic, like sample variances and things like that, and he provided a framework that only uses Chebyshev's inequality and doesn't really require independence that gives you these types of scalings. But thank you very much for this question. Helped me clarify a lot. Yes, there's another one. That's a very good question. He's asking if there's any results where D is not an integer. I'm not aware of any, and I also wouldn't know how to produce them myself, to be honest. So it's a very interesting question, because, for example, square roots would be very interesting if you want to estimate concurrences or more general fidelities. But I don't know how to do that. except from doing a Taylor approximation and using these things, which is cheating, I guess. Thank you. Okay, so far, we've only looked at a very general Monte Carlo sampling techniques, and so I have never assumed anything about the state. And when I assumed something about the observables, it was only that they're maybe local or something, or low weight, but we never really took into account the actual structure of an observable, and we never really took into account that most states have some additional structure. So far, our results were fully general, and now I want to tell you a bit about further improvements that you can achieve if you make assumptions on either the types of target functions you're interested in, or the state, or the quantum hardware. And so the first thing that comes to mind is structure in target observables. This randomized measurement strategy, if we now think about the single qubit measurements, the tensor products, which is what you would do to estimate many Hamiltonian terms in the near term, there on the second slide I told you the randomized measurement strategy doesn't care about the actual terms in the Hamiltonian, it only cares about their weight. And then you kind of like just do random sampling and hope for the best. But this is not always possible, especially if you look at quantum chemistry applications of near-term quantum computers, right? If you try to map a fermionic system into an n-qubit device to solve some interesting quantum chemistry ground state, for instance, you typically do some sort of encoding, like a Jordan-Wigner encoding or a Bravik-Kitaev encoding, and the resulting terms in your Hamiltonian are very structured. They are tensor products of Pauli matrices, but what they are not is low weight. Like a Jordan-Wigner encoding has a lot of z terms before the 1x minus y term comes, and a Bravik-Kitaev encoding doesn't have a y Pauli matrix at all. So you would be stupid to actually perform a y measurement in the data acquisition stage if you're interested in a Bravik-Kitaev encoding. But what is definitely true is in these cases, uniform Pauli sampling is bad. Because just think of one string in Jordan-Wigner, the probability of hitting that would be very small if you choose every single Pauli matrix at random. But of course, this is probably not what you should do, because in practice you should care about what you actually want to estimate. And the first solution to this problem was pointed out early in 2020, very quickly after the formalism appeared for the first time, and they proposed a very intuitive solution. If you know something about the target observables, then you shouldn't sample X, Y, or Z with the same probability. Uniform sampling across X, Y, or Z is just a statement of ignorance. You don't care about what you measure, you don't know it, and so you do everything equally often. But in practice, if your Hamiltonian terms have way more X than Y operators, then you should sample X more frequently than Y. And this is something you can do simply by adjusting your Monte Carlo sampling strategy. Don't choose every Pauli matrix with the same probability. And this is the first solution, which actually works surprisingly well. Here on the right-hand side, you see a plot of a typical quantum chemistry application where we ask ourselves, how big is the estimation error for some quantum chemistry ground state energy? I think we did some Jordan-Wigner encoding here, as a function of the number of Monte Carlo samples I take, the number of measurement repetitions within each VQE loop. And you can see that the standard randomized measurements performed rather poorly. The y-axis is in Hartree, actually, so 1 is good. This is not the actual 1, it's in the right units. And these bias distributions by the IBM group immediately got it down to this green line. And what is a bit more interesting, I don't want to go into details, but they also came up with a tractable preprocessing algorithm that takes into account the Hamiltonian terms you actually care about, maybe the Jordan-Wigner encoding, and outputs biased single qubit probability distributions for your measurements that really reduce the variance and therefore increase the accuracy when you want to estimate the full Hamiltonian. They have an interesting, efficient algorithm for that. And there's another way, which is arguably more greedy, and this is something that Robert, John, and myself developed, is to use a technique from classical probability theory called de-randomization to start with an initially randomized measurement setting and squeeze out the randomness to get a deterministic measurement procedure that works at least as well. And this is another way, which is algorithmically tractable, to reduce the estimation error if you want to predict many terms that are not necessarily local. And there's another way of viewing this de-randomization technique as a greedy strategy of trying to measure the best Pauli observables I can. Like if I start my first measurement with the first qubit, x, y, or z, I can have a look at the terms I actually want to predict to decide whether it's better to do an x, y, or z measurement. For example, if my Hamiltonian doesn't have any y terms, I probably shouldn't use a Pauli y on the first qubit to begin with. And then you can insist on this choice of measurement and compute the chance of, if you continue to assign all the other measurements uniformly at random, do I still get all the terms correctly? And this future chance of winning depends on the choice I'm doing now. For example, if I assign my first measurement to be a y operator and none of the targets have a Pauli y, then I've lost regardless whatever I'm going to do. But if I choose an x or a z, I still have a chance of winning, and there's actual ways to compute these chances of winning quickly and efficiently. And if you know to compute at each step of your measurement, you have three choices, x, y, or z. And if you know the chance of winning for each of them, if you continue to play randomly, then there will be a smallest one, and you can always choose that. And then you go through the entire measurement process and always replace an initially random Pauli matrix by the Pauli matrix that maximizes your chances on getting everything as often as possible, given that you play randomly in the future. And that's another way of squeezing out randomness and getting very, very concrete deterministic Pauli measurements that perform even better. It's the blue line here. Okay, both solutions come with efficient algorithms. That's important. If you know your Hamiltonian, you can run either of the two and get a much better measurement strategy, but the actual estimation is the same. It just depends, it just affects your choice of random measurements. And yes, on a higher level, the take-home message is, if you know something about the target functions you're interested in, you better use it. And there are here are two ways to take into account information if you're, for example, interested in VQE applications in quantum chemistry. This is for free, for instance. Careful. If you use these techniques, you're interfering with the twirl invariance for robustness I mentioned earlier. So this is no free lunch. If you actually highly bias your measurements, then your measurement noise will not be washed out. Just be mindful of that. Yes?
If you're looking at non-linear functions, like full stop changing this,
Very good question. He asked, what if you're looking at non-linear functions? Does this change anything of this? The answer is probably. I don't know a result yet. So far, these results only address linear functions. This is uncharted territory. Thank you very much. Yes, Earl?
If you're interested in chemistry problems, could you not use like the free fermionic group instead of the group?
So Earl suggests to actually use physical insights about quantum chemistry, like the fact that this is fermions, to use some different type of randomized measurements, right? Like you mentioned, the fermionic group. And I think the answer is maybe. I'm out of my depth here, but I think this is totally possible, to come up with a new way of doing Monte Carlo sampling that takes the problem more seriously than these approaches actually do. I think this is a very good point. Yes?
There's a question from Daniel Tan. He says, is there a difference between de-randomized and manually designing the measurement? In the beginning, you said manual design is hard in general.
Sorry, can you say that again? What is the two options?
Okay, I'll read the question again. It just says that, is there a difference between de-randomized and manually designing the measurement?
Yes. The de-randomized measurement strategy is just one way, one greedy algorithm of coming up with a certain measurement design. It's one solution to the measurement design problem that is based on a greedy single qubit update. This makes it efficient, but also prone to be stuck in local minima. It's one heuristics to solve the more general measurement design problem. Thank you very much. That was a very good question. Okay, yes?
Like the solution one that is mentioned here, like does it also provide an automatic way of like biasing the measurement, or you have to like, reduce the bias pattern?
Well, what he's asking is where the bias comes from. Is this correct?
Yeah, like in solution one,
Yes.
like do we have to manually design the bias distribution, or like it also provides an automatic way of coming up with the bias distribution?
So what he's asking is where the biases come from. And this is a very interesting question. And what they actually proposed in their efficient solution is to again do a pre-calibration stage where you now have, let's say, like 3 degrees of freedom. One of them is the state, the other one is the target functions, and the new degree of freedom is the bias in your single qubit measurements. Now you know the target observables. What you don't know yet is the state. And what they are proposing is to use a classically known state that is close. For instance, you calibrate your estimation procedure on the best classical solution to your quantum chemistry problem mapped onto a quantum state. And if you fix a state that is close by and you fix the target functions, then the convergence, kind of like the degree of convergence, can be measured by the variance, and the variance now only depends on the bias. And they propose an efficient algorithm to do just that and give you 3 numbers that you should then use in your randomized measurement strategy that gets you much better. Is this an answer to your question? Thank you very much. I think this was also useful for all of us. And now we know that if we actually take target observables seriously, we can get significant improvements. Symmetry would suggest that the same should be true if we make assumptions about the underlying state, right? And let me just re-emphasize that if we only are interested in very low weight observables or Hamiltonian terms where the weight is constant, 2, 3, or 4, then what our randomized strategy actually provides, the Monte Carlo sampling technique tells you if you do order log L over epsilon squared, many randomized measurements, you can get all L of these low weight Hamiltonian terms epsilon accurately, right? But in general, this is localized information about a big system. And in general, localized information is not enough to fully reconstruct the state, right? Just think about topological order, for instance. And so this is not a complete strategy for determining the full underlying state. We only get localized signatures. But for certain state classes, localized information is enough to actually fully reconstruct a description of the entire state. The most famous example are Gibbs states. If you know that the underlying state is a Gibbs state, and you know the corresponding Hamiltonian, and you also know the inverse temperature beta, then in principle, localized information is enough to reconstruct the coefficients in front of the Hamiltonian, which is a problem known as Hamiltonian learning. And the question is, if I now give you slightly noisy approximations of, sorry, this should be an HL here, of each, the expectation value of your Gibbs state for each of the Hamiltonian terms that are involved in the Gibbs state, then the question of Hamiltonian learning is, can I use this noisy information to piece together the full state or learn the actual Hamiltonian this localized statistics belongs to? That's the question of Hamiltonian learning, and it can be solved, and I think this is very exciting. Just as a heads up, because I find this very interesting, the difficulty of the Hamiltonian learning problem depends on the inverse temperature beta. If beta is very high, that means the temperature is very low, and our Gibbs states can be close to ground states of Hamiltonians, and we believe that those are difficult to learn and patch together based on localized information. And here you can actually see an empirical plot from a paper by Anurag Anshu et al., where you can see that the cost actually really goes up when the inverse temperature becomes large. Surprisingly, this problem is also very difficult if the inverse temperature is close to 0, because this means that we have a very high temperature Gibbs state, and it will look almost like the maximally mixed state. And now the task is, I provide you local expectation values of something that almost looks like the maximally mixed state, determine the actual coefficients. That's also very difficult. And so the feasible regime for Hamiltonian learning is really in the regime of low but not too low inverse temperature. And there's 2 recent solutions to this Hamiltonian learning problem that both use information of this form. Expectation values of terms of the Hamiltonians, and the randomized measurement toolbox can provide just that. And now you can use that as a pre-processing step to do these Hamiltonian learning problems. And the first solution to this Hamiltonian learning problem that came up with really nice convergence guarantees and sampling rates proposed to use the maximum entropy principle, Jane's principle. If you know approximately what all the local terms should look like in your Gibbs state, you can vary the parameters in your Hamiltonian to find the largest entropy Gibbs state that is compatible with all the localized features that we already know. And this is an optimization problem, and they show that if you can actually solve that, they show that it is in principle solvable, and they also point out that the number of samples they need to get sufficiently accurate approximation of these individual Hamiltonian terms scales roughly like this, which is polynomial in the number of Hamiltonian terms and not exponential in system size. So I'm sweeping a lot under the rug, but what they are telling you is if you know that you have a Gibbs state and if you know the Hamiltonian and the inverse temperature, then you can use localized information that randomized measurements provide you. For instance, there's other ways of getting them, to piece together the full Hamiltonian and by extension the state based on a number of measurements that is essentially quadratic in the number of terms. And recently, this was improved by, it's like in a very similar mindset, but different mathematical techniques by Zhonwu Ha, Robin Kothari, and Iwin Teng. And what they are proposing is to not use the maximum entropy in principle to solve these problems, but they come up with very accurate Taylor expansions of the actual observables as polynomials in nu. In principle, you can write down a Taylor approximation of each Gibbs state, and they show that this converges quicker than what you would think. And you can approximate the matrix exponential by a polynomial. And so these things become polynomials themselves. And if you now are interested in the parameters, the problem reduces to solving a system of polynomial equations. And if the inverse temperature is not too high, then they show that a Newton-Raphson method actually converges, and the number of measurements they need is only logarithmic in the number of terms. So this even goes quicker, and for certain Gibbs states, this with inverse temperature not too high, you can actually run this algorithm in principle. And so, at least if you assume that the underlying state is a Gibbs state, you can use localized information potentially provided by Monte Carlo samples to piece together a full description of the state. And you can do that in some sense, sometimes even efficiently. And so the take-home message really is, if you have additional structure in the underlying state, you can either get substantial performance improvements if you want to estimate many local properties. I didn't talk about that yet. But maybe the localized information allows you to learn much, much more. In this case, the entire Hamiltonian of the Gibbs state. And I think this is also a very interesting, timely research problem. What happens if we assume that the underlying states have a certain structure? Can we either speed up the randomized measurement procedure or use localized information that randomized measurements provide us with to learn strictly more than just local features? This is one example of this kind. And no talk about randomized measurements would be complete without mentioning the possibility and potential power of stronger quantum hardware. Like what I now explained, the Monte Carlo technique, is you use very, very NISQ-friendly measurement settings. You prepare the state, you do a simple unitary rotation, you do a measurement. But of course, this is not the most powerful thing we could envision to do with a far-term quantum computer. It is known that these types of problems become much easier to solve and more efficient to solve if you don't perform measurements on independent copies of the quantum state, but if you store multiple copies of them in a quantum memory and do entangling measurements that correlate all of them. This is a strictly more powerful measurement setup that is in principle feasible with far-term quantum computers, where you can ask the question, how far can I go if I really use the full power of a far-term quantum computer for these types of questions? And this is exactly what Scott did in 2018 when he coined the term shadow tomography and actually gave rise to many of these ideas that I explained to you. And what he set out to is to ask the question, how many state copies, in the far-term sense, do I need to epsilon approximate a collection of L2 outcome probabilities? That's a state learning question. You want to get as kind of like, you want to have an algorithm that allows you to predict how an unknown quantum state will behave if you use them in your experiments. And what he could show is that the number of samples of state copies now that you need in order to solve this goal depends polylogarithmically on L, the number of probabilities or observables you want to predict, logarithmic in the Hilbert space dimension, 2 to the n, and like an inverse of the fifth power in the number of state copies. And note that this really is exponentially better than all the Monte Carlo guarantees I presented to you so far in some worst case regimes. Here you don't have to assume that your target functions are local. You don't have to assume that they are that they have small Hilbert-Schmidt norm, for instance. This is just unconditionally true. The downside, I don't know if it's a downside, it's just a general result about far-term quantum computers. In order to actually execute the procedure, you would really need a far-term quantum computer and have to be able to store many copies of the unknown state in parallel in it. But if you can do that, there's a lot of room for improvement. And I think I will skip the proof idea, actually, in the interest of time. Maybe many of you have already heard excellent talks by Scott explaining that. I just want to point out a recent beautiful refinement of the original proof strategy by Badescu and O'Donnell, who managed to reduce the polylog factor in the number of targets you have. But also what they really did is they kind of made the entire strategy that was arguably already hidden in Aronson's first paper a bit more accessible for people, for a broad audience. So kind of they really clarified many of the steps that were already there and put them into a new order that didn't only yield improvements, but makes it arguably also a bit easier to follow. If you're interested in that, Ryan O'Donnell has an excellent YouTube talk that is worth watching, where he points out how you can get these types of improvements with far-term quantum computers. But the take-home message is definitely, if we have quantum memory and if we have entangling circuits, then we can do strictly more things, and these strictly more things are really empowering and can yield exponential improvements in certain scenarios. Here, just a very quick slide for synergies with machine learning. You can use these Monte Carlo samples to generate classical descriptions or approximations in form of bits that somehow carry some structure of the underlying quantum system. For example, it allows you to compute local properties, maybe correlation functions. It's all in the Monte Carlo data. And we have seen results that tell you that you can choose certain functions and you could estimate them in order to learn something about the underlying state. But it doesn't have to be you who decides what to measure. You could also delegate the selection of what are the relevant properties for the problem I'm actually interested in to a machine. You could combine these Monte Carlo sampling techniques. You could use them as an intermediate link, as a quantum to classical converter to wire a quantum computer that generates training data to a classical algorithm that performs machine learning for certain tasks, like solving the Hamiltonian ground state problem. And here, Monte Carlo samples can really allow you to efficiently use quantum to classical converters to use quantum states as actual training data, then converting them into bit strings that with high probability maintain the information below that can then be exploited by a machine learning network. But I don't want to say much more about that because Robert is going to give a talk here, and I highly encourage you to attend it in order to see how we can use these Monte Carlo sampling techniques to empower machine learning. And this is we are almost at the end. I think this is one of the most beautiful and most important contribution to this entire field of Monte Carlo sampling, fundamental lower bounds. So far, thank you very much for paying attention. I've spent almost my entire talk trying to convince you that these simple Monte Carlo techniques are very powerful. They have many promising applications, and they're also simple, which is a good thing. But a natural question is, are they really that good? After all, we don't use additional information in the easiest regime. We do just independent measurements. We do Monte Carlo is not something very sophisticated. What about lower bounds? What is the performance of these relatively simple, tractable Monte Carlo techniques in practice? How much room is there for improvement? And interestingly, kind of the results we derived are very far away from an unconditional lower bound that was presented by Scott in 2018. So Scott showed that regardless how powerful your quantum device is, if you want to predict L properties up to accuracy epsilon, then you will need at least a number of measurements or samples or state copies that scales logarithmically in L and inverse quadratically in epsilon. And this is much smaller than everything you saw on my slides, because we always had a dependence on the actual target observables or properties we're interested in. This is not here. What is more interesting and closer to home is what happens if you don't do unconditional lower bounds, but assume something about the quantum hardware that is available to you. One thing is to assume that you're only allowed to do measurements on individual state copies. The assumption is no quantum memory. You have to prepare the states, measure it, and then prepare it again and measure again. A sequentiality assumption. That's what I mean by single copy measurements. And another assumption you can make, but maybe you shouldn't, is to assume that your estimation strategy is non-adaptive. The Monte Carlo techniques are non-adaptive because at each step you do exactly the same time. You don't pause and try to learn something from the things you've seen by adjusting your measurement description. If you also assume this non-adaptiveness, then you can prove an information theoretical lower bound that actually exactly saturates the results we derived in the first lecture. The proof idea dates back to a beautiful paper by Steve Lamia, David Gross, Yika Liu, and Jens Eisert from 2012, where they kind of use quantum state estimation techniques more broadly as a subroutine in a communication protocol between Alice and Bob, where Alice encodes classical information into a quantum state, sends copies of the quantum state to Bob, and now it's up to Bob's resolution of his experimental process how much information they can convey over the entire channel. If Bob's device is very powerful and has a very high resolution, they can use very dense codebooks and convey a lot of information. If it's not, if the resolution is not that good, the codebook must be smaller. And then you can use fundamental lower bounds from quantum information theory, like Kolevo's theorem, to come up with fundamental lower bounds that if you write them out in the right scenario, give you bounds like this. What does this tell you? If you're willing to do non-adaptive measurements and you only have access to single copy, then in the worst case, these Monte Carlo sampling techniques are as good as it gets. Don't expect any outlandish improvements. They are not possible. But these are really some strong assumptions, right? Except especially the non-adaptive assumption is kind of nasty. And here's where beautiful recent ideas come into play by Robert Huang, Jordan Kotler, Sitan Chen, and Jerry Lee. It's very new, but they came up with a completely new proof idea that also allows you to cover adaptive single copy measurements. So we still have no quantum memory, but now we're allowed to be smart and actually learn from the experiments. And what they showed is that the lower bound that there's also a fundamental lower bound that doesn't look too different either. There's a different exponent now, but also kind of it's a different regime, if I may say so. But the Monte Carlo sampling techniques we discussed earlier, surprisingly, also saturate this bound. And so this is more interesting because it kind of shows you that non-adaptive Monte Carlo sampling is, in the worst case, almost as good as adaptive strategies where you're allowed to change the measurement setup whenever you wish. as long as you don't have a quantum memory. And the proof idea, I think, is really nice. It models a full classical learning algorithm that learns from these experiments in the form as a decision tree. In the beginning, before you have done any measurement, you don't know anything, and that's the root of your tree. And then you perform a measurement of your choosing, and then you get an outcome, and depending on that outcome, you traverse down the tree. And so in the next layer, you record the measurement you did and the outcome you obtained. And now, conditional on your position in the tree, you can keep on going down by performing the second experiment and so on. And if you're given a measurement budget M, you will end up with a rooted tree whose depth is M. And if you perform your adaptive measurement procedure, you will go down this tree along a certain path. And at the end, at the leaves, they can be associated with certain probabilities of ending up in that leaf. What is the probability of my learning algorithm doing kind of this zigzag walk on the tree and ending up at a certain leaf? And these probabilities depend on the state, right? You can think about that. The state affects the transition probabilities, and this will affect the probabilities at the leaves. And now, what these folks have essentially shown, I'm simplifying a lot here, is that unless the tree gets very, very deep, the total variational distance of the leaf distribution is very small for drastically different states. An intuitive example is, first, you look at this leaf probability distributions for the maximally mixed state, where essentially like every transition probability is uniform if you do a reasonable measurement. And so kind of it will be a uniform distribution. And the other extreme case is, for example, a highly complex state, a Haar random state. Then also, adaptively, like kind of whatever single copy measurements you will do, if you don't know the Haar random state, they will also almost look flat. And so the leaf probabilities will look very similar. And if you actually want to be able to distinguish hypothesis 1, it's the maximally mixed state, from hypothesis 2, it's a pure state, but a Haar random one, with any adaptive learning algorithm, the leaf probabilities need to be substantially different. And this can be controlled by the total variational distance. And what they actually showed is that there's many reasonable examples, much more reasonable examples than the one I gave just now, where the total variational distance between the leaf probabilities remains tiny until the tree size becomes exponentially large. And the tree is one way, the tree structure is one way of dealing with adaptive measurements. And this is, in a nutshell, how they get this lower bound. And this really shows that Monte Carlo sampling, which is independent, is in the worst case is kind of not much worse than more sophisticated adaptive measurement strategies. And what I also want to point out is that these kind of almost saturating lower bounds for Monte Carlo sampling techniques all assume that you only do single copy measurements. If you have access to a quantum memory, like in Scott's shadow tomography, the rules are completely different, and you can get substantial improvements again. But they hinge on availability of quantum memories. Okay? So the take-home message is these Monte Carlo sampling techniques saturate fundamental lower bounds, but you have to be a bit careful about the details when you try to compare the upper bounds with lower bounds. And just very quickly, because I'm running out of time, but I think this is a very interesting recent development, is new types of quantum advantages from these lower bounds, actually. Because what I've done so far is I've tried to explain and cover successful applications of simple Monte Carlo sampling techniques. And the lower bounds on the last slide, at least for single copy measurements, tell you that often Monte Carlo sampling is almost the best you can do. And so it's interesting to look at problems where Monte Carlo sampling is bad. Because intuitively, if there's a matching lower bound, then maybe any estimation procedure that uses single copy measurements will struggle with that. And so it's arguably almost more interesting to look at examples where Monte Carlo sampling fails than at successful examples, because this shows you that something interesting might happen. And a difficult challenge for Monte Carlo sampling is the task of simultaneously predict many non-local Pauli observables. And this shouldn't come as a surprise, because Pauli matrices mostly anti-commute n-qubit Paulis, and that means that you can't measure them jointly. And so when you only can do single copy measurements, you in a way have to decide which Paulis you prioritize, and then there's always a lot of Paulis where you don't know anything about. And this is a feature of the Monte Carlo sampling techniques, because for predicting many Pauli observables, both the single qubit random unitaries and the scrambling unitaries perform pretty bad. But the lower bounds tell you that even adaptive single copy measurement strategies wouldn't be much better. So kind of predicting or learning features about many Pauli observables is probably a difficult task for any learning algorithm that only uses single copy measurements. And interestingly, for this Pauli challenge, a quantum memory where you can store 2 copies of the quantum state can already make a huge difference. And why is that? I actually want to use the whiteboard one last time. Intuitively, it makes quick sense, actually, because why is estimating many different Pauli observables difficult if you only have single qubit measurements? Because 2 given Pauli operators typically don't commute. There's way more Pauli matrices that don't commute than that commute. But here's something interesting. If I take the tensor product of any 2 Pauli operators, sorry, with tensor power 2, if I tensor any Pauli operator with itself, the Pauli operators commute. Just because Pauli is either anti-commute or commute, and if I take the tensor product, I can get rid of the minus sign. But this tells you that if you had access to two copies of your state, a small quantum memory where you can store 2 copies of your state, you could measure these tensor product observables, and you could measure them all at the same time. And this would then allow you to predict the square of these things, which tell you how large the absolute value is. You don't know the sign, but you can estimate the magnitude if you have 2 copy measurements. And this was pointed out, kind of like these ideas were pointed out in one paper by Robert, John, and myself, and also similar ideas were pointed out at the same time by Dorit Aranov, Jordan Kotler, and I forgot the first name of Key, for other types of challenges where single copy measurements are necessarily bad, but 2 copy measurements already can make a big difference. And recently, we all joined forces, and it was really mainly Robert Huang, the Google group, Jordan Kotler, and a lot of other people actually, who used these ideas to come up with NISQ-ready challenges. Like find a variant of this problem, learn something about many different Pauli operators that doesn't involve actually questioning about many Pauli operators, but is only a challenge, where I prepare 1 of 2 states, for instance, I give them to you, and I ask you, after you've done the experiments, which Pauli observable is larger. But basically, there's a framework of turning these ideas into a challenge for quantum learning, for learning many properties, where having access to 2 copies of your state can make a huge difference. And the challenge was easy enough to implement on the Google Sycamore chip. And you can see the results on the right-hand side, where this really is the fundamental lower bound from 2 slides before that tells you that for these types of challenges, you need exponentially many resources without quantum memory. This is what Monte Carlo sampling would give you, and these are actual data points taken from the Sycamore chip that executes the smarter estimation procedure on 2 copies. And so I think this is, a really interesting and nice result. And so I really think it pays off if you have a new tool to play around with to carefully look at where it fails. Sometimes the failures are more interesting than the possible results because they can point towards a new type of quantum advantage. And with that, I'm actually done, and I want to wrap up. As a conclusion, I think we're really living in interesting times where we can use quantum devices to prepare interesting quantum mechanical systems that were inaccessible to us just 3 years ago. But at the same time, we don't have direct access to the density matrices. We can only sample from the distributions. And this seems like an annoyance. But if you combine it or view it through the lens of Monte Carlo sampling, which is still a highly competitive numerical solutions in many applications, this inconvenience becomes a distinct advantage. Because Monte Carlo sampling has as bottleneck the sampling process. And the sampling process is exactly that, what quantum computers can do well. And if you combine these two ideas, you get a formalism that gives you tractable and highly efficient learning protocols that can be equipped with rigorous performance guarantees. And I also think that these ideas can form a bridge between rigorous quantum information theory, which is the core strength of QIP, which is why we're here, but also more practical NISQ applications and even experiments. I focused more on theoretical aspects today, but it would have been totally possible to give a similar talk with a lot of experimental explanations, experimental demonstration, and so on. What I want to point out is that this can really bridge, I think, one community with the other, and is interesting for that reason. And with that, I also want to close with a small advertisement. If you're interested in these types of things, like many smart people have joined forces to write a review article about the randomized measurement toolbox, and I think it should be out on the archive soon. Please have a look if you're interested, but also feel free to reach out to me. Thank you very much. And I'm happy to take questions if there's some. Yes, Victor.
In the beginning, you showed how to get something difficult out of the sum of easy
Yes.
things. But when you went to the quantum picture, your easy things were slightly off. They were biased toward
Yes.
maximum mix. Is that a fundamental thing? Can you get rid of it?
Okay, that's a very good question. Thank you, Victor. Kind of to remind it for the people on Zoom, I started off with explaining a Monte Carlo sampling as taking an object and exactly decomposing this object into a sum of simple terms. And then when we looked at the quantum measurement processes, things got slightly skewed because we started off with a Monte Carlo estimator that looked reasonable, and then we found out that it was distorted and biased towards the maximally mixed state. And then I said you have to compensate for that by undoing this bias effect. And so kind of we don't, arguably there's like a bit of a conflict with the original Monte Carlo idea, but on a high level, this entire computation of the average, together with the inversion of the bias, can be viewed as finding the right probability distribution with how to weigh the simple objects. This was part of the first step, and thank you for giving me the opportunity to clarify that. The first step in a Monte Carlo approximation is to find a decomposition into simple terms that is weighted so that I can actually sample. And computing these wrong averages and undoing them can be viewed as one way of solving this question. Yes?
I have a question about this bipartite scenario you mentioned.
Yes?
How hard is it to perform this measurement?
You're talking about this plot? Here?
Yeah.
Okay.
Like, so you have this situation in two documents that overcome this bottleneck.
Yes.
And I'm asking, like, how to implement this measurement.
He's asking how the two-copy measurements should look like that actually overcome this bottleneck. And the answer is it's Bell basis measurements on individual copies. So if you have n qubits, you put them next to each other, and you perform Bell basis measurements. And I leave it as a homework for you to figure out that you can actually estimate all of these tensor products by doing a single Bell basis measurement. But it's really easy. Yes?
Yeah, I was wondering, in the multiple copy scenario, is it equally well understood how to construct the measurements and process them to estimate these output rules? Because, for instance, I remember the paper on the sycamore experiment uses a neural network to predict observable from the data measurements. So I was wondering, because it's not as well understood as in the stereoscopic case, or is it because of something else?
He's asking like why many approaches use machine learning techniques to address these
Why do you
types.
think of a paper specifically by Robert and others uses that?
Exactly, why machine learning techniques? Like the first answer is just empirically they perform better. And the reason for that is that this is at least my explanation, I'm not the best machine learning expert, but I think if you actually do some training, then there's some noise mitigation happening in the background. I think when neural networks, even if there's a simple linear solution, which there would be for these types of experiments, if you still train a neural network, there will be some error mitigation effects. Okay. But yeah, in principle, there would be simpler explicit algorithms to solve all of these subroutines here, but they would be more susceptible to noise. Okay. Very good question, thank you. Yes?
If you apply this randomization procedure of the random poly measurement to the initial height, for example, do you obtain the, again, like the optimal measure all x, measure all y, and measure all z?
That's a very good question. So what you're proposing is to do 2 copy measurements to get... in the de-randomization, yes, exactly. Actually, that was the first sanity check we did. If you do this type of, I think it's even in the appendix of the original paper. If you do de-randomization. Yeah, thank you. Sorry, I forgot. What he asked is, suppose I use this de-randomization procedure, which was one way of improving the measurement setup in the case where you know the observables, like here. What happens if you insert the Heisenberg-Hamiltonian example from the second slide? Do you get the right answer? And for the de-randomization technique, the answer is yes. Because in the first step, you have x, y, and z terms. If you make your first decision, it doesn't matter if you choose x, y, or z. But if you put down your cards and say it was x, then you can only lose if you measure y afterwards. And the de-randomization algorithm tells you that. And then you stick to x. Thank you.
I'm sorry, I'm going to have to interrupt at this point because unfortunately it's my duty to keep time and we're kind of done.
Yes.
So, sorry. That was it.
So we're done. Thank you.